Hello and good evening, everyone. Today I'm speaking to Nate Nikolov and Carl Ziller. They are two independent researchers. And the topic of this conversation is the greenhouse defect. And that will become clear as we start talking. So first, Nate and Carl, welcome to the channel.
Thank you for having us.
Yep. All right, so first I want to get, what is your background? I mean, this is obviously atmospheric science, but how did you two get into it? Because you're labeled as independent researchers, right?
Yes, I work for the U.S. Forest Service, which is a government agency part of the United States Department of Agriculture in the United States. But this work I have done on my own because I was instructed by my employer early on to not use the Forest Service as an affiliation, and just to, if I want to work on climate, to do it on my own time. And this is what I has been doing, including the papers that we publish, conferences that we have attended, and so forth. I have a PhD in ecosystem modeling. My background is basically, my PhD was on modeling and understanding the interaction between the terrestrial ecosystems and the atmosphere, exchange of energy and trace gases, including CO2. And then this was a long time ago. I did my dissertation in 1997, and then I switched to working in the area of fire weather. So fire weather is how the weather impacts the fire behavior, and specifically developing applications where the weather forecast data being processed in a way to give some useful indices for the people that are fighting the wildfires, and give an indication about fire danger, what's going to happen over the next, between 3 and 7 days, because that's what the forecasts are good for, the operational forecast. So based on the forecast data, we develop applications that actually give indication to the fire professionals, to the fire managers, and the people on the ground, how what will be the fire danger, how the fire danger situation evolves over the next week or so.
And specifically for prescribed burns,
Right.
for managing prescribed burns.
Prescribed burns and wildfires, all of them. So just as a background, so Carl Zeller was I'm right now a manager of a project that deals with fire weather and developing applications based on fire weather. But Carl Zeller was the former manager of that program, and he retired 2008. And then 2010, I was working that program already for about 10 years. But 2010, I kind of inherited his position, not inherited, but I applied for the open position, so I got the job. And I basically inherited his work, and we went from there. So,
okay. And how did you get them from fire to greenhouse effect? If we can jump.
Well, as you know, weather and climate are kind of brother and sister, right?
Yeah.
I mean, they're basically, climate is kind of the average weather, or what they say. Climate is what you expect, and the weather is what you get. Being in the weather, in the forecasting of fire weather, I started working with climatological data, and I just have interest in meteorology in general. Although this was not my background, but I have a strong background in quantitative modeling of ecosystem atmosphere interactions. And then back in 2009, when those emails were leaked, the ClimateGate emails. And I started reading through that. It made an impression on me that there was something that they were trying to hide. They were not straightforward coming with the data and the 4 requests and all that. At that time, I thought that the science is settled. I believed in the greenhouse effect and all that. So I got curious, and I started, decided to go into the science papers and figure out. I had some questions that were in my mind about that time, and I thought, within a few months of reading, I'll answer my questions. That will be it. I satisfied my curiosity. Well, it turned out that after 6 months, I had a lot more questions than in the beginning, and I started realizing that those things, as described in the theory, do not add up. I was not convinced politically that this is the right thing, and if something is not right, I would not pay attention to it. If anything doesn't add up, I would go and read more about this to inform myself, to educate myself, and try to make sense of the whole thing. Well, the more I read, the more I realized that things do not make sense in a physical sense,
And according to the establishment, you're not allowed to change your mind on any of these topics. This is a taboo topic. And,
well, that's what they say officially. I think a lot of scientists do realize that there are problems, but they don't have the courage to acknowledge it publicly, because the funding depends, their funding depends on supporting that theory. Maybe in the past they have written papers, they have built careers on that. So all of a sudden to say, well, I'm sorry, now we were wrong. It takes a lot of courage to do that. But there are scientists that actually can do that, maybe not in climate science as much as in other fields. But if you do that, actually, you may gain more reputation and more popularity. The problem with climate science is that the whole thing is controlled by the funding of science, and funding of science is strictly along political lines. So if you deviate a little bit, you're risking of losing your funding. If you lose your funding in your university, your career goes to a stop, right?
Yeah.
Comes to a stop. So
that was the point that General Eisenhower made in his last farewell speech. Where he said eventually public policy is going to be held captive by a scientific technocratic elite. And the problem is if the elite is following a particular dogma. Dogmas are assertions that they're not to be challenged. Global warming is one of them. There are other ones that I've dealt with on this channel. As soon as you step into that bounds, you get kicked out of the political elite. You get kicked out of the establishment, and they replace you with somebody that does respect the dogma. So this is where science moves from science to what is called scientism, right? It stops being science and turns more into theology. So I want to direct us into the conversation today. To say it is the greenhouse effect, but to understand the greenhouse effect, firstly, it's my belief that it is entirely dumbed down in public discourse. And when you dumb down science, you see the rise of incompetency. So whenever somebody says it's a blanket around the Earth, they're not really being honest. They're trying to get people to understand complexity through simplistic notions. And that's dangerous sometimes, because then you can have people with a lot of confidence speaking about something they actually don't know about. So let's get into it. The first one is the concept of black body radiation. According to Boltzmann's law, there is a relationship between the amount of watt that an object emits and the temperature to root 4. Now, if you do that calculation for the Earth, you find out that the theoretical black body radiation temperature of the Earth is to minus 23 degrees Celsius, around there.
It's about minus 18, but
minus 18. Okay, it's minus 18, and then there's obviously a difference. We don't live in minus 18 degrees, right? And this difference is usually ascribed towards the so-called atmospheric greenhouse effect. So can you maybe explain to us what is the greenhouse effect as is understood by traditional dogma?
Well, I think I explained this in details in my video, just for the viewers to be aware of. There is a video called Demystifying the Atmospheric Greenhouse Effect. It's available on Vimeo. Maybe you can provide a link at some point. Also on YouTube. The YouTube channel that video can be found is Truth and Insights. Insights is with like a plural with S, because there's another channel apparently, Truth and Insight, which is religious, not to be mixed with that. But Truth and Insights, I have a few videos there on the climate, and the most recent one is called Demystifying the Atmospheric Greenhouse Effect. So in that video, I do explain actually what is the current mainstream view about the greenhouse effect. But in a nutshell, the greenhouse effect is viewed to be a radiative phenomenon. That means it is caused by the long-wave radiation coming down from the atmosphere. And conceptually, the atmosphere is, actually, this is in the official literature, that the atmosphere traps heat. That's the name, the term is being used by IPCC. They also use the term heat-trapping gases, referring to the so-called greenhouse gases, which is CO2, methane, ozone, nitrous oxide, and so forth. But the idea is that, yeah, the atmosphere kind of works like a blanket, although they do say that the blanket prevents, cooling by obstructing the convection, by obstructing the mixing of air under the blanket and outside the blanket. So they say the atmosphere works in a different way, but the different way that they ascribe to the atmosphere is basically that there's a trapping of infrared radiation, not a mass of gas, but the infrared radiation. And so the idea is that the Earth gets heated by the sun. It emits radiation out upwards, towards the space. This radiation gets intercepted by so-called greenhouse gases because they absorb long-wave radiation, which is, it's a physical fact that's true. And part of this radiation is being sent back to the surface, and this accounts for so-called trapping of radiation. So it's like a flux is coming out, it gets absorbed, and part of it is sent back. So when you look logically, say, oh yeah, okay, so part of the energy comes back, and that's how the atmosphere works to heat the surface above the temperature of the moon, for example, which is, moon is a body that is the same distance from the sun, but has no atmosphere. It's much, much colder. And so that's the overall idea, that the greenhouse effect works basically by, they use the word trapping, or another word that they say it's more precise is the reducing the rate of energy loss to space, basically reducing the rate of cooling. Some people say, no, there is no trapping, but the rate of cooling is being reduced, right? So, which is another form of trapping, if you think about it. And the problem is that when you look at the actual data of the energy fluxes coming from the atmosphere, from the lower atmosphere to the surface, and then the total energy that's coming from the sun, that we absorb from the sun, you get the situation where the flux, this is observed data, those are real, the energy flux, long wave radiation coming from the atmosphere towards the surface, it's in the order of 342 watts per square meter global average, right?
That's from the atmosphere towards the surface, 340.
Right.
Yeah.
Basically from the lower atmosphere towards the surface. This is what the surface sees in terms of long wave flux from the atmosphere.
Right.
Well, the problem is that the total amount of radiation absorbed from the sun by the atmosphere and the surface is in the order of 240 watts. So you have about like a 43% more energy coming from the atmosphere down than everything that has been absorbed from the sun.
Yeah.
So if you look at the explanation of the greenhouse theory, what they claim, how the atmospheric warming works, this explanation violates the first law of thermodynamics, which is the energy conservation law, because you could not get 342 watts downward radiation from 240 absorbed from the sun. It's like how this magnification happens. We're talking about amplification of energy, right? How this happens? Well, if you say that it happens because you have a absorption and re-radiation multiple times, that doesn't work. Like I mentioned in the video, if you have two bank accounts with certain amount of money, and you start to transferring money between the accounts, and you lose after every transaction, you lose a little bit of money. You could not increase the amount of money in both accounts because you're doing the transaction back and forth, right? Because that's how the energy conservation law works. You have a certain amount of energy. By moving the energy from one place to another, you could not increase total amount of energy in the system. Therefore, the explanation provided by the greenhouse theory for the large downwelling infrared flux from the atmosphere towards the surface must be incorrect. This flux is not caused by the absorption and re-emission of radiant heat by greenhouse gases as claimed by the current climate theory.
So how does traditional atmospheric physics or climate science describe the seeming contradiction that the greenhouse effect might violate the first law of thermodynamics?
That question has never been addressed. In fact, if you bring it up to a climate scientist, they will say, no, there is no such thing. There is no violation of any law. Everything is correct. And when I asked them those questions, I have asked this question about those fluxes, the downwelling flux of the long wave radiation compared to total absorbed flux from the sun, 342 compared to 240. I said, how the 240 becomes 342? Most scientists have not even thought about this. And they say, well, there has to be an explanation somewhere, but it doesn't really matter what happens inside the atmosphere. What's important is on the top of the atmosphere, you have a balance. 240 coming out, 240 coming in, and 240 coming out. I said, yeah, but how does things get magnified down at the surface? Because that's where we're experiencing the warming and everything. That's where the thermal effect of the atmosphere is experienced at the surface, not on the top of the troposphere. And when I have pressed a number of climate scientists, including recently, I had an interaction with Kevin Trenberg. He's one of the top climate scientists at Anchor in Boulder. We had an email exchange, and I asked him that question. He could not answer the question. Not only that he tried to avoid the question, just dodge it completely, and not even come to, I pressed him different ways. I tried him to acknowledge that this is an issue that is not answered in the greenhouse theory, and he refused to even go there. So
the traditional view, let me put it this way, the debate between climate alarmism and climate skepticism, if I can use those two words, has always been climate sensitivity. They are arguing in 2050, 2100, how much heat are we getting? And those who are skeptical say, look, this is going to be nothing of an issue. Those who are alarmist are saying it's going to be the end of times, or anything from 2 to 7 degrees from the IPCC, right? You two have gone further, and you have said this is something we are totally missing the boat here, because there are anomalies that are not being addressed. So you're saying that the greenhouse effect, and I'm now using the word thermal enhancement, which is being used in your paper. So the reason there's a difference between the black body temperature and the Earth's temperature, that's the thermal enhancement. That's traditionally called the greenhouse effect. But to understand you two directly, you're saying that theory itself has got holes into it, and you're proposing an alternative, right?
But let me say something at this point. Okay, so adding to the side of what Ned said, you can call the atmosphere around the Earth a blanket. It's a very thick blanket. Okay, so it is, the full atmosphere is the blanket. And at the very basic, you have a molecule of oxygen, or a molecule of carbon dioxide, or nitrogen, or methane. That molecule, there's basic physics. That molecule has a engineering term called absorptivity. And it has another engineering term called emissivity. Okay. And this gets into the Stefan Boltzmann relationship.
Right.
But so you have a molecule of, say, oxygen, and versus a molecule of carbon dioxide. And they're sitting there in the atmosphere at a given level. We do know that the atmosphere cools off as you go up. Okay, that's called lapse rate. So at any given level, there's these two molecules sitting side by side, and both are going to absorb the long-wave radiation coming from wherever, from around it. Some's coming from below, some's coming from above. Both are going to absorb the long-wave radiation. Now, it turns out that the absorptivity of any given molecule is equal to its emissivity.
Correct. Kirchhoff's law,
It's
right?
the same number. And there we are. We absorb something, but we instantaneously emit what we absorb. And what we emit is based on the basic temperature of the environment that we're in. Now, relating to the Stefan Boltzmann law, that's a big deal here. And that's where you get your minus 18 degrees, and the greenhouse gas effect is 33 degrees. That's based on a simple calculation using the Stefan Boltzmann law, which says that these two molecules sitting here next to each other are at a certain temperature. You know, let's give a number. I don't know, maybe they're 300 degrees Kelvin or something like that, right? So now the Stefan Boltzmann law says that they're going to radiate proportionally to the fourth, to take the temperature that they are, to the power of 4, where they're going to absorb and emit is related to that temperature. That's how the Stefan Boltzmann law fits into all this. Now, on top of this, in high school, some of us learn the gas laws. There's Boyle's law, Gay-Lusiak's law, Charles'
Ideal gas law, yeah.
And there's you put all those together and you come up with the ideal gas law. Now, the ideal gas law, you know, the one easy way to think about it is pressure times volume divided by temperature. And and that's in any given parcel of air. In the basic physics of a molecule absorbing and emitting, there's nothing in there about storage. The thing about the blanket is the blanket does not have any physical lid on it.
Yeah.
So it is allowed to expand and contract. Okay, so I just wanted to give that basic understanding of the atmosphere that I don't think people think about.
To answer the Hugo's question about the greenhouse effect, how it's calculated, so it's basically the difference between the current temperature on the Earth, global average temperature, and the temperature without greenhouse gases or without atmosphere. In the current theory, if you have no greenhouse gases in an atmosphere, like you have only, say, nitrogen and oxygen, which is pretty much the case in the Earth's atmosphere, we have a small amount of greenhouse gases, but if you take those out, the current theory thinks that the temperature of the Earth will drop to minus 18 degrees Celsius. You can still have the nitrogen and oxygen, but if you take out the greenhouse gases, which are trace gases, it'll be the same as if you have no atmosphere. Now, this is the first thing that is totally physically wrong. I mean, it's like 100% wrong.
Let me interrupt there. That's why I went through all that background. I wanted to give the background of what Ned's talking about now, in that those molecules are not different. The greenhouse gas molecules and the ones that are not called greenhouse gas molecules, there's no difference. They're actually
they're not different in the gas law. That's correct.
Yeah,
the gas law
all greenhouse gas. Okay.
The problem is that when they're comparing those two temperatures, so the first thing that they do is that they say greenhouse gases, if they're removed, it's like you're removing the entire atmosphere, the same effect. The second problem is that they claim that without the atmosphere, without greenhouse gases, which is the same thing in the greenhouse theory, the Earth's temperature will be minus 18 degrees Celsius. This minus 18 degrees Celsius is a calculated number from the Stefan Boltzmann radiation law that connects the temperature to the energy flux of the system, right? So the problem is that this law applies to isothermal surfaces. That means the surface that has the same temperature over the entire surface. The law is correct, but it applies to isothermal surfaces. The Earth is not an isothermal surface because it's a sphere. When you have a sphere, you have different illumination on the equator compared to the poles, right? And so then the temperature changes accordingly between the equator and the pole. So you have a heterothermal surface. In order to calculate the average temperature of a sphere, you need to actually do a spherical integration of the Stefan Boltzmann law to get the average, spherically average temperature of an object that has, the shape of a ball, like a planet, right? So the greenhouse theory, what they have been doing for over 50 years is that they take the average absorbed radiation that's coming from the sun, say 240 watts per square meter. They apply the Stefan Boltzmann law, which is only valid for isothermal surfaces, and they calculate a temperature, and this temperature is the minus 18 degrees Celsius that we're talking about.
Yeah.
Essentially, it's a temperature of a flat disk. So here we have the temperature of the Earth, which is measured, spherically average temperature on the surface of the Earth, which is about 14 degrees Celsius, right? And you're comparing this temperature with the temperature of a flat disk above the atmosphere, right? Those two things like apple and oranges. So if you subtract 14 degrees average spherical temperature for the Earth from the flat temperature that is calculated from the Stefan Boltzmann law, you're subtracting a spherically average temperature. You're subtracting
you cannot relate the two.
The two are apples and oranges. The difference between those two temperatures have no physical meaning. This is the subject of our first paper that was published in 2014, where we make this, the mathematical explanation is this called Hölderlin inequality between integrals, but it's a mouthful. It basically says that you could not compare the temperature of a flat disk to the spherically average temperature and take the difference and think that this is something meaningful. It has no meaning. So the 33 degree or so of atmospheric thermal effect calculated that way, it's mathematically wrong and physically wrong. So then the question arises, how much is the actual thermal effect of the Earth's atmosphere if it's not 33 degrees, right? Well, in order to answer this, what we have done is we created another model which was verified against the temperature of the moon, which is the moon basically is a perfect airless equivalent of the Earth. because it has the same distance from the sun but has no atmosphere. So you want to compare the temperature of a body that has no atmosphere to the temperature of Earth with the atmosphere, compare the surface temperatures of both of those two bodies that are spherically averaged. They are not like flat disk in a sphere, but they're both spheres, right? So we developed a model which basically was an integration, spherical integration of Stefan Boltzmann Law of a sphere. We came up with a new formula that gives you the temperature of an airless body, the temperature with no, well, a body that has no atmosphere, right? And we compared this to the data from the moon, and the model was verified against those data. So now when you subtract the moon temperature from the average temperature of the Earth, basically the temperature of an airless body to that from that of a body with atmosphere, what you get is about 90-degree difference. And this is actually the true thermal effect of the Earth's atmosphere. It's about 90 degrees, not 33 degrees.
So is it minus 80, minus 90, or plus 90?
No, the difference is 90 degrees, but the average temperature, absolute temperature of the moon is in the order of 197 Kelvin. Okay, so when you take the difference on the average temperature on the Earth is about 287.4 degrees minus the 197, so you end up with roughly about 90-degree difference.
Yeah.
So the presence of atmosphere on Earth, when you do the calculations correctly, not only physically correctly, but you compare with the temperature of the moon, which is the real airless equivalent of Earth, right? You get the estimate of the thermal effect of the atmosphere, which is 2.7 times higher.
Would that then be a cooling effect or a heating effect?
It heats the surface always, right?
Okay.
The fact that we have an atmosphere does not make us 33 degrees warmer.
Yeah.
It makes us 90 degrees warmer.
Okay, makes us 90 degrees warmer.
And other planets with different atmospheres, it would make it different amounts warmer. People listening in, Ned was talking about the Stefan Boltzmann approach to a flat disk. Well, to be correct, the energy coming to that flat disk is distributed isothermally around a globe. So he's talking about the energy calculated with the isothermal energy put on the globe versus the integration of the different temperatures. That's what he's talking about. It is a sphere related to sphere, but it's how the energy was distributed and how the Stefan Boltzmann law was applied to each infinitesimal point on that sphere.
So basically, the Stefan Boltzmann law is used to calculate the temperature at every point on the sphere, and then you do the integration by taking into account that the area, say, around the equator is much larger than the area around the poles. So that's why the spherical integration comes into play, because if you have an average temperature on the equator, say, of 213 Kelvin, and on the poles it's 80 Kelvin, you don't average those two to get the average temperature, because the area around the equator is much bigger than the area on the poles. So you do the weighted average. So spherical integration, basically, it's a weighted average. So now the 90-degree thermal effect poses a problem, because the known energy budgets of the Earth, basically long wave radiation down, long radiation up. Incidentally, this is very important to note, is that the greenhouse effect in the current theory, has two definitions. One definition is the 33-degree or 90-degree that we talked about in terms of temperature, right? The heating effect on the surface. The other definition, which the greenhouse theory considers primary one, is the flux difference between the long wave radiation coming from the surface and the one measured on the top of the atmosphere. Yeah. So in real numbers for the Earth, about 398 watts per square meter are coming out from the surface. And on the top of the atmosphere that's coming out to space, it's about 240. So the difference is like 159 watts per square meter, right? This is the flux difference between the surface and top of the atmosphere. That flux difference in the current theory, in the greenhouse theory, is considered the greenhouse effect itself. Why? Because they consider the greenhouse effect to be a radiative phenomenon. So the primary definition is to the energy flux, not to the temperature difference. Temperature difference, they say, it's kind of a secondary. It's like a byproduct, right? Well, if you take the 159 watts per square meter flux difference between the surface and top of the atmosphere, this could not explain the 90-degree thermal effect, because we already established that 90 degrees is the real number. This is not 30 degrees, it's 90 degrees the real number. It could not explain because this radiation flux is not sufficient to do that. This definition of the greenhouse effect as a flux difference is basically irrelevant with respect to surface warming. That has no relationship. And the way this actually was proven, there were a couple of papers published by different teams, not us, one in 2015 and one in 2018, where they used this flux difference as a definition of the greenhouse effect over Antarctica. And this definition yields 0 or negative greenhouse effect of Antarctica.
That's strange.
So, in other words, Antarctica is supposed to have what, the temperature of the south pole of the moon or something? No.
Yeah.
The difference between the temperature between south pole of the moon and the center of Antarctica is something like 144 Kelvin. It's a huge number, right? And in fact, when you do a comparison of the temperature profiles on Earth on the surface, starting from the equator and going to the poles, and then you compare this with the same temperature profile of the moon, equator to the poles, and you do the difference between the two, that is the true atmospheric effect, how it changes with latitudes, right? And what you find is that the thermal effect of the poles is actually, by the atmosphere, is the largest. The smallest effect is on the equator. And the flux-based definition of the greenhouse effect gives the exact opposite. The highest amount of absorption of radiation is at the equator, and the smallest amount is at the poles. So this flux definition of the greenhouse effect does not even have any relationship to the actual warming on the surface, none.
So the measurement contradicts basically.
The very basic definition of the greenhouse effect, as defined in the peer-reviewed literature, makes no physical sense with respect to the actual warming experienced by the surface that is caused by the atmosphere.
You're saying the black body radiation, the Boltzmann constant law, the temperature they use as reference for the Earth is derived for a disk. That's obviously not true. The Earth is a sphere. Okay.
Yeah.
And the second one, you're saying that there are actual temperature measurements that show that at the poles and at the equators, the temperature is showing, and the radiation flux is showing opposite to what the greenhouse theory would predict. Is that correct?
Right.
So on this radiation difference between the surface and the top of the atmosphere, just think about what we're measuring. Basically, if you're measuring radiation flux, you're measuring the temperature of the surrounding atmosphere. So you're sitting there measuring how much long-wave radiation is coming out of the Earth. You're measuring at that specific point what the temperature is below it, due to the Stefan Boltzmann law. That's the radiation that you're measuring. Okay, so that's a point measurement. Okay, and if you go further up in the atmosphere, you're going to measure a different number, smaller number, and as you go up, finally at the top, you're going to measure that 240 watts balance. So comparing what you're measuring at the very top to the very bottom, that doesn't even make any logical, to compare those two numbers doesn't make any logical sense. And that's why what Ed is talking about is so important, is so like breakthrough thinking or understanding.
So I want to now ask on the third thing about the greenhouse effect before we move to what you propose, and that is the concept that the radiating height, if I remember now correctly, radiating altitude, I believe it's called, changes as we add CO2 to the atmosphere. That's now according to the standard theory.
That's a fiction.
Maybe explain. Can you maybe explain that theory first?
That's just a mathematical fiction, and Ned loves to talk about this.
So so this is at length described actually in the movie Demystifying Atmospheric Greenhouse Effect that I mentioned at the beginning. But basically, the claim is that the greenhouse gases increase the opacity of the atmosphere to long-wave radiation. So the more of those gases you have in the atmosphere, the more the atmosphere becomes opaque, meaning that lesser amount of radiation, long-wave radiation from the surface goes straight to space, and most of the radiation actually gets absorbed first by the gases, then re-radiated. Some of it goes to space, some of it comes back. That's how the theory goes, at least. And so the idea is that when you increase the opacity of the atmosphere, what happens is that, before just let me explain this, that the minus 18 degrees Celsius that we talked about, that is thought to be the temperature of the Earth without greenhouse gases. This number, this temperature actually happens to appear in about 5.5 kilometer altitude above the surface of the Earth, in the atmosphere. And so the thinking is like, because this is the temperature that corresponds to the Stefan Boltzmann radiation that the Earth all emits to space, this temperature that appears at 5.5 kilometer has to be something that this is the place where most of long-wave radiation is coming out to space. It's like the source, right?
Right.
So because the surface also has some radiations coming directly from the surface to the space, but it's small fraction. Most of this, the radiation is coming actually from this altitude, because this is the altitude where the minus 18 degrees Celsius appears, right? In reality.
Yes.
So
that's the idea. That's the theory.
So that's the idea. So this elevation, this altitude is called effective emission altitude.
Right.
So now the theory goes, and it's not a theory, actually it's a thought experiment, because this mechanism was proposed 120 years ago by Niels Ekholm, who was a friend of Svante Arrhenius, and he just presented in a paper like a thought experiment. He has no data, he had no physical theory behind that. It was just a thought, and he put it in there, and it started to be repeated, and then all of a sudden now it's an established science. That's one of the strange things. Yeah, it becomes a dogma. But anyways, the idea is that as you increase the opacity of the atmosphere by adding more greenhouse gases, this effective radiating level, altitude, goes up. So the temperature, the effective temperature is still minus 18 degree or minus 20 degree, whatever the number is, but it starts to be emitted from a higher altitude now. And by doing that, they say, okay, now the lapse rate, which is the change of temperature from high altitude to the surface, which is temperature from the high altitude to the surface, increases about 6 degrees per kilometer, right? If you change this altitude where the radiation is coming out to space, you automatically apply the lapse rate of a longer distance, and you have warming on the surface.
Assuming the slope stays the same, yes.
Yeah, the slope is the same. So the lapse rate is kind of fixed because of other reasons. But this mechanism is absolutely artificial from a physics standpoint of view, because as I pointed in the video, in order to change the temperature of a gas mixture, you need one of two processes. One is called diabatic process, which means adding energy from the outside, from an external source like the sun, adding more energy to the system in order to raise the temperature. The other one is called adiabatic process, which means increasing the internal pressure. Those are the only two mechanisms that one can knows in the physics, in the standard physics, that can change or increase the temperature of a layer of air close to the surface. And here we have a mechanism that is basically the temperature is being changed at the surface due to some geometry. You just change the distance over which you apply the lapse rate. And I explained this in my video that the height of a temperature layer in the atmosphere, it's coupled tightly to the height of a pressure level, because the reason why in the troposphere the temperature drops with altitude, from the surface to going to about 10 kilometers, so it drops with altitude. It's because temperature depends on pressure, and pressure decreases with elevation. So that's why you have the drop of the and this is the reason why we have the lapse rate. But this mechanism that suggests that you just artificially change the distance over which you apply the lapse rate of 6 degrees per kilometer, and this is causing the warming. It has no relevance with the actual physics of the atmosphere. And the other thing is that in order to change the temperature level in the pressure level, which they're connected, right, in the atmosphere, to raise it higher, you need to either increase the surface temperature, or you have to increase total pressure, or you have to lower the gravity. Those are the three things that the physics, the thermodynamics of the atmosphere, that is well established, and there is no question about that, says it needs to happen. In other words, the height of the temperature layer in the troposphere is a function of the surface temperature. It's not a driver of it, it's a function of it. It depends on it. You see?
Mm.
So this whole concept in the greenhouse theory is basically backwards.
So it seems to violate, correct me if I'm wrong here, almost the ideal gas law as well. From that
Well,
point of view.
it violates, like I said, the fundamental principles of physics, that in order to change the temperature of a system, gaseous system or otherwise, you need to have one of two processes, or both of them, either adiabatic heating, which is adding energy from an external source, or adiabatic heating, which is increasing the internal pressure of the system. Those are the only two ways you can change the temperature. You could not, do some kind of a tricks with the geometry, like in this case it's proposed, in order to change the temperature. The point is that when you go back in history and you see where this idea comes from, which was exactly 120 years ago, published, expressed in a paper by this guy Niels Ekholm, without any physical theory behind it, without any experimental data, or any, they didn't have any data back then about, the vertical change of temperature in the atmosphere, or any satellite data, anything like that. They didn't have anything, basically. This thing was just proposed as a thought experiment. When you don't have any data, you're allowed to speculate, and in science that's fine. That's how you propose a theory. Once you get the data, if the data show that what you thought was correct or mechanism doesn't work, you have to admit that your suggestion, your thought experiment was wrong, and you move on from there. Well, this hasn't happened in reality. In reality, what happened is that this idea has been repeated, and now it's considered part of the standard greenhouse theory. And like I have the video clip on my video with interview with this climate scientist. His name is Raymond Perehumer. He's right now at Oxford University. He's expert in radiative transfer. He explains this as this is an established science. There is nothing established behind us. There is no data that support it. This is just a thought experiment that was proposed 120 years ago, has been repeated 18 times by generations.
It's still conjecture at this stage. It's not been.
Well, we know from our physics that we know today that this is plain wrong.
Yeah. Okay. So that is a big. That to me is a big violation of physical laws.
So let me add something. So basically, in real life, what Ned is saying, that in order to increase this height, this effective emission height, either one of two things has to happen. Either we get more energy from the sun, or we get a higher pressure on the surface, which means more atmosphere.
Or you lower the gravity, which is not possible.
Say again? Or the loss. Oh, excuse me. Yes, or the loss of gravity.
You're saying, if you sum it up, the greenhouse effect, as currently understood, is more dogma than science, right? I want to just ask a last question on this, and you explained this also in your video, and Carl touched a bit on this earlier. Explain the Kirchhoff law, maybe, and how that does not relate to gases. With how
the Kirchhoff law does relate to gases.
Okay.
It basically says that under equilibrium conditions, emissivity equals absorptivity. Now, the other thing in relation to the greenhouse effect is that there is another radiative property of material objects with respect to infrared radiation called reflectivity. So reflectivity is basically, this is what hard materials like, with metals and stuff like that. Reflectivity is 1 minus the absorptivity. So if the absorptivity, say, for example, is absorptivity and emissivity are equal. So if you have a 95% absorptivity emissivity, the reflectivity would be 5%, because you have 100 minus 95, you have a 5% reflectivity, right? So the thing is with gases is that the gases do not reflect long wave radiation. Hard material objects do reflect long wave radiation, like the solar reflects a little bit, tiny amount, but things like aluminum, polished silver, gold, they reflect a lot of long wave radiation because their emissivity or absorptivity is very small.
Yeah.
So in order to trap, when you're talking about trapping radiation, infrared radiation, space, this trapping is possible, but it requires those types of materials that have high reflectivity and very low absorptivity with respect to long wave. Those are not gases. They're like materials like aluminum, silver, and gold. and aluminum has been used. They call it radiative barrier. The foils of aluminum has been used in buildings between the roof and in the attic, between the bottom of the roof and the top of the roof inside. So those aluminum sheets, they reflect back long wave radiation inside and also outside. So basically, this is another form of thermal insulation. Okay.
Right.
But the point is that those materials have the exact opposite radiative properties as the gases, the greenhouse gases. So any material that has high absorptivity and emissivity of long wave radiation, it promotes cooling, it promotes the transfer of heat. It doesn't trap heat. The trapping can only happen with materials that can reflect. So in my view, I make a strong point about difference between reflection and re-radiation. Re-radiation is when the material object absorbs energy from incoming energy from another object, but then what it emits is like it depends on its own temperature. It doesn't emit back the same flux. It emits based on its own temperature, right? So the flux may be different. There will be a spectral difference and also difference in the actual magnitude of the flux. So it's not like a one-to-one, Reflection is like the radiation is getting reflected back with the same strength as the one that's coming in, and there is no absorption. So the object that reflects the amount of radiation that's being reflected, it does not affect the temperature of the object. When re-radiation, it affects the temperature of the object. So it's a whole different process. The bottom line is that, without going into the weeds, is that the trapping of radiation, long wave radiation, requires materials that can reflect long wave radiation, and gases are none of those materials. Gases do not reflect.
So the Earth's atmosphere does not have the mechanism to trap the heat.
Exactly.
So that's the other anomaly, I would say, in the greenhouse theory. Okay.
Another important aspect of the atmosphere is that, forget about the radiative properties of gases, is that the atmosphere has convection. And convection, advection, that means the transfer of heat through fluid motion, and that's the most efficient way to transfer heat. And when it's an open system, doesn't have a lid on it, the convection is not being hampered or impeded, right? So basically, because of that, the atmosphere cannot trap heat. It's impossible because it's an open system and it's convective. The air is moving. When you have hot air on the surface, it moves up and it cools, adiabatically or with exchanging of heat with the surrounding air. But there is always motion.
Right.
The transfer heat from the surface up high.
Okay, so those are all the I would say the questions that you two had, regarding the greenhouse effect, and so the claim is you dispute the traditional theory, right? Now, first, my understanding is that this dispute is not actually a new one. It goes back. I've read somewhere that even Maxwell had some questions about the greenhouse theory. Is that correct?
I think Maxwell. There was a discussion between Maxwell and who was in Boltzmann. What will happen if you have a column of air that has a pressure gradient, right? If the column is like equilibrium temperature, would the column have the same temperature throughout the length, or the temperature will decrease with height because the pressure decreases, right? So I think that Maxwell said that the temperature will decrease with height. This is exactly what's observed in the current atmosphere. In the current standard atmospheric thermodynamics, there is no dispute about this. The people that know
anyone who's gone up a mountain shouldn't dispute it.
Yeah. So there is a decrease of temperature with elevation, and this is caused by the drop of pressure with height. There's no dispute about that. So this part is solved. It's not. Right. But the greenhouse theory kind of is silent about this. When you ask people, climate scientists, well, what's causing the temperature to drop with altitude as you go higher? Some of them would say because they run those radiative transfer models that have no convection in them, just only radiative transfer. And using those models, you do get something that's similar to the lapse rate, very steep decrease of temperature as you go with height. And this is produced by the radiation. They think that the radiation is the one that's causing that. But reality is not like that at all. It's not the radiation, it's the temperature drops with height because temperature depends on pressure, and pressure decreases with elevation. And therefore, the temperature drops also with elevation. The long wave radiation, then, is just a product of the temperature. Because any material object, including gases, when they have temperature above absolute zero, which basically the entire universe, they emit radiation. This is actually part of the Stefan Boltzmann Law that says that any material object with a temperature above absolute zero, which is pretty much everything in the universe, even in the deepest corners of space, the temperature is still above zero. It's not really zero. Maybe, a fraction of a Kelvin or something, but it's still above zero. So all material objects, they emit radiation, and depending on the temperature, this could be long wave radiation, could be visible radiation, could be ultraviolet. The higher the temperature, the energy spectrum is moving towards the shorter wavelength. And so when you have the sun that has a temperature of 6,000 Kelvin, it emits light that we can see and it has warmth that we can feel. But if you look at the moon or the earth, they have a lot lower temperature. They emit radiation that we could not see. That's why it's called long wave infrared radiation.
Okay, so now I want to go to us to recap. So we are now at the point where you say you dispute the greenhouse effect, and you've made the statement that there are lots of anomalies in the theory, that the theory is very bad at explaining all these, the lapse rate particularly is one big question mark, behind the theory. Now, what is your explanation for why the Earth is as warm as it is? The difference.
Let me interrupt right here.
Yeah.
We do not dispute it. We have a discovery that basically shows that the greenhouse gas theory is incorrect.
Okay.
We have a discovery, not necessarily a theory.
Okay. So you're
okay. We'll come to that in a minute. Yeah, we'll come to that in a minute. So your question was about what's causing the thermal effect of the atmosphere. If it's not the greenhouse gases, right? So, like Carl said, we, in order to answer this question, when we realize that it's not the thermal radiation, because the thermal radiation does not match with the absorbed solar radiation, so you have this amplification effect at the surface. And if you look at the radiative transfer only, without looking at anything else, you could not explain this amplification without violating the first law of thermodynamics, which is the energy conservation law. From 240 watts per square meter of absorbed radiation, you could not get to 342 at the surface. There has to be a mechanism that amplifies this energy. What is this mechanism? So it's not the energy transfer, because energy transfer could not do that. There is something else. So in order to answer the question, what is this something else, we decided to use data from NASA, temperature data and atmospheric data of a range of planets and moons in the solar system that are well studied, and we have good data for them. And we decided to apply a technique called dimensional analysis, which is the objective method to derive physically meaningful relationships from empirical data without knowing anything about the theory.
Engineers know dimensional analysis quite well, because whenever you struggle in an exam and you don't know what the units is, you just use fractions to balance the units out, and then you get the final answer.
Right. Yeah.
And that's the principle, the basic principle of dimensional analysis.
Right.
Is you let the units go to the basic unit. So you can say everything is mass, but speed is distance over time. Whether it's meter per second, kilometer per hour, it doesn't matter how you work with it. That's the principle of dimensional analysis. And that's the principle by which most of our scientific units are derived.
A way to incidentally, it's called the Buckingham Eye Theorem. That's what allows you, or that theorem points to doing a dimensional analysis. Dimensional means it doesn't have any units. I call them God units. In other words, God doesn't measure things in feet or meters. It's a unit, and it's usually a ratio. It's some kind of a ratio.
Yeah.
So dimensional analysis, what it allows you is to reduce the number of variables that you have into a smaller number, much smaller number of variables. That in the Buckingham Eye Theorem actually comes there. That gives you the number of variables that you can reduce from n dimensions to a smaller number. And then those numbers that you have, then they are dimensionless ratios. They are ratios of different. So basically, when you look at the dependent variable, independent variable, they both have no units. They're dimensionless. Like temperature divided by temperature is no units. Distance divided by distance is no unit, right? So by converting all the variables you're studying a phenomenon, and you have all these parameters that you don't know how they're related, but you convert them into dimensionless units, and then you start looking into dimensionless units to see how they relate to each other, and then you discover relationships that actually this is how nature operates, because in nature, natural laws, they operate with dimensionless units, because the nature doesn't have any preference to kilograms or pounds or whatever, those are human dimensions.
It's ratios at best, but yes.
The ratios are the ones that the nature operates on. So anyways, we applied this technique. We used the NASA data for 6 planets. Those were all the planets with solid surfaces for which we had good quality data available. And once we applied dimensional analysis, what it turned out is that it's all described on 22 pages, long paper, technical paper. But the bottom line is that we discovered that there is a continuum throughout the solar system that explains the surface temperatures long term. We have to point this out. They're not annual temperatures. They're not even decadal, but they are long term, like a number of decades, average temperatures on planets and moons. And those temperatures can be explained with only 2 variables. This is the result from dimensional analysis: solar radiation coming to the planet, or distance from the sun, if you want to say another way, and total atmospheric pressure. No composition, nothing else. Well, the composition of the atmosphere, we have those 6 planets that we looked at. The range of atmospheres and their compositions was very wide, like from no atmosphere to the moon to like 93 bars of atmosphere on Venus, and anything in between. So it was a huge range, and all these very diverse planets, from very close to the sun to very far from the sun, their temperature, the average global surface temperatures, were totally explained with a very high accuracy by 2 variables: distance from the sun and total pressure. So what we discovered is that the atmospheric thermal effect, not only on Earth but on any other planet and moon that has atmosphere, is caused by the pressure itself. So it's a thermodynamic phenomenon. It does not depend on the composition of the atmosphere. And that was a big discovery, because everybody in the greenhouse theory knows that they all focus on the composition. They're focusing on tiny greenhouse gases. The CO2 is the control knob of Earth's climate, blah blah blah. And we say now, wait a minute, the data, the continuum that exists in the solar system, which is not just Earth. Earth is part of that continuum at one point, but the whole continuum that is described by those planets, using better data from NASA, it shows that the thermal effect of the atmosphere is 100% due to pressure, and it's a thermodynamic phenomena, not a radiative phenomena. Nothing to do with radiative properties of gases. It's all pressure.
So when you say it doesn't have anything to do with the composition of the atmosphere, but obviously the weight of the air, if you go down, doesn't that in a way depend on the amount, the composition of the atmosphere and the molar mass of the atmosphere as well?
Well, it depends on the mass of the atmosphere, yes.
Yeah.
But that doesn't depend if this mass is made out of, if you have the same number of the same amount of mass, like X, you call it whatever number is, you can have that mass composed of pure carbon dioxide, you can have it composed of pure nitrogen, you can have it composed of pure oxygen. As long as the mass is the same, it doesn't matter what kind of gas you have.
But I mean, I'm just reasoning from the point of view now that gases have different molecular masses. So obviously the thickness of the atmosphere is in a sense irrelevant.
Oh yeah,
for the same gas, the thickness of the atmosphere will change.
The volume will change, exactly. The volume will change. When you have, for example, you have nitrogen compared to pure nitrogen atmosphere compared to pure CO2 atmosphere, carbon dioxide atmosphere, because carbon dioxide is heavier with the same gravity. A pure carbon dioxide atmosphere will have will have a smaller thickness, a smaller volume rather, which means a smaller thickness, but a smaller volume than the atmosphere that's composed of pure nitrogen. But as long as the pressure on the surface is the same in both cases, the temperature will be the same as well. So it doesn't matter when you have a nitrogen or you have a carbon dioxide, you have the same temperature as long as the pressure of the surface is the same. The volume of the atmosphere is something that depends on the heating. You can take Earth and put it at the orbit of Titan, right? the atmosphere will shrink because it's so little radiation reaching, almost like 1,000 times less radiation reaching Titan than reaches the Earth right now. So if you go to the orbit of Titan, the same atmosphere that is now on Earth, you move it over there, the same pressure and everything, because of the small heating from the sun, the volume will shrink. And so, the density of the surface will increase quite a bit, maybe like, about 4.5 times. But the volume will shrink as well because that's how the density increases. So the volume is something that depends on the level of heating, the amount of radiation coming from the sun. It doesn't depend on the total pressure. You can have two different atmospheres, very different volume with the same pressure on the surface.
Okay.
Can you see how blasphemous this is? In other words, Earth is not a special case.
It's part of the continuum.
Water doesn't mean anything. I mean, it certainly does. We can't live without it. But this puts us exactly, this puts us kind of where we were back in the days of Copernicus, where Earth was a special case. And
so the greenhouse effect. But I want to now taste this a little bit. Throw a few caveats at you. If you go take the proxy record of temperatures, okay, there's obvious fluctuations in the Earth's temperature. How do you explain this then?
We have two videos that are on my channel that actually address this issue. One is about the new insights from our model, from our discovery, the implications of that for new understanding of the drivers of paleoclimate. When I say paleoclimate, I'm talking about climate change, changes in global temperature that occurs on timescales of thousands to millions of years. And then we have a separate video that talks about the short-term changes in climate that are on annual to decadal scale, or maybe annual to centuries, right? Like a few years to a century, to a few centuries. The mechanisms that are driving the climate change on those two timescales are very different according to what our findings. When the greenhouse theory tries to explain everything with carbon dioxide is a driver on a time scale of 60 million years. Carbon dioxide is a driver on a time scale of last 40 years. It's all the same driver, right?
Yeah.
Well, on a longer term, they talk a little bit about the Milankovitch cycles, which is the orbital variations, blah, blah, blah. But the orbital variations...
Well, some people would say the sunspot activity and all these things also play.
Well, the sunspot activity, it's not even in the climate theory. In the greenhouse theory, it's not even there.
Yeah, look, I even under the current theory, I'm not with the alarmist crowd. I'm very skeptical that it might just not be the sun. Okay, but obviously yours is a little bit counter narrative to all of that. So I'm just trying to relate the pressure phenomenon. Obviously there is sun cycles, sunspots still occur. I mean, that has to have an effect, doesn't it?
Magnetic activity of the sunspots are manifestation of that. But the magnetic activity of the sun has some impact. And right now there are different theories, and there is experimental evidence that supports one of those theories. But the specific mechanism is not well known. It's not in the models. And this impact is that the sun, through its magnetic activity, impacts the cloud formation, impacts the nucleation in the cloud. So therefore, when you have the empirical observation is that when you have a highly active sun, like we had over the last 150 years, the amount of clouds that on the Earth decreased a little bit, and we're talking about a few percentage points, not like a lot, right? But that's enough to increase the amount of radiation reaching the surface of the Earth, which is the reason for the warming. The clouds, they reflect the radiation back to space. So the more clouds you have, the more reflection you have back to space, so less radiation reaches the surface. When you increase the cloud cover, the net effect of the cloud is to cause cooling. When you decrease the cloud cover, the net effect is to cause warming because more radiation reaches the surface. So the satellite data that we have available since 1979 will clearly show that it has been, and this is not disputed anymore, there's a bunch of papers written, not our research, including NASA scientists and university scientists and so forth. The cloud cover has decreased over the last 40 years. And the decrease is such that the amount of radiation that has increased at the surface because of this decrease in the cloud cover is more than enough to explain the entire warming that we have observed. You don't need to invoke any CO2. The problem is that the CO2 story is based on climate models, which cannot simulate this cloud dynamics. The cloud, they have changes in the cloud.
I'm trying to put this now in perspective of your theory, because you have been saying that the Earth's warming, or the solar system, that the planets in the solar system is not a radiator phenomenon. It depends on the distance of the sun, and it depends on the gas, on the
Right.
weight of the atmosphere, basically.
Right.
But now I'm trying to say, what would happen then, given this theory, if the sun and the cloud formation, how does that relate to the temperature of the Earth? Was it irrelevant in a sense?
So one of our videos that I have in my channel specifically talks about this. It's an extension of our model that includes the cloud albedo. The reflection of radiation from the clouds is called albedo, and it includes the effect of cloud albedo as an extension to the model. So from our basic model that says the long-term temperature of any planet is a function only of solar radiation reaching the planet on the top of the atmosphere and total pressure, how about the temperature that is part of this long-term, but it has the fluctuations like on an annual, decadal basis, even on a centennial basis, you have those fluctuations. So what are the drivers for those? What we have concluded from our analysis is that variations of the global temperature around a long-term baseline determined by solar irradiance and atmospheric pressure are caused by fluctuations of cloud albedo induced by sun's magnetic activity. Using the extension of our model to predict albedo effects on surface temperature, which was verified against satellite measurements by CIRRUS for the past 20 years, this conclusion allowed us to reconstruct variations of Earth's albedo for the past 2,000 years.
Just for the listeners, if they have followed it to know, albedo is the percentage reflected, basically.
It's the fraction of radiation that is being reflected back to space. And
Right.
that radiation from the sun coming to the Earth that reflected back to space does not impact the climate system because it does not enter into the climate system. It just boom, goes back, right? It's a pure reflection.
And Team Panic says that if the ice melts, the albedo will decrease. The Earth will absorb more radiation. We're all going to burn. That's basically
yeah, but there is another story into that if you melt the ice, what happens, you increase the evaporation from the surface. When you increase the evaporation, you increase the cloud cover on the top. So this idea that the lack of ice is causing the albedo to drop, maybe in some small areas, but overall, it's not the case. And I'll tell you, there was a very interesting paper that was published a few years ago called the Albedo of Earth. In another recent paper published in 2021, they looked from satellite data, and the authors, they were amazed to discover that, they look at the two hemispheres, right? The northern and the southern hemisphere. Now, everybody knows that the northern hemisphere has a lot more land mass, a lot more deserts and stuff like that. So the albedo on the surface of the northern hemisphere is much higher than in the southern hemisphere, because southern hemisphere is more ocean, right? You have the Southern Ocean, and you have Antarctica, which is has a high albedo, but then you have this huge area of ocean that is very dark surface, right? So the albedo is low. What they discovered is that looking at satellite data, that the difference between the reflected radiation between the northern and southern hemisphere, it's only about like a 0.2 watts per square meter. Very minimal. Why? Because the clouds, they compensate. The clouds act as a offset of whatever the difference is in the surface albedo. This is not the final thing. The final thing is how the clouds will respond. And so, although we have so different albedos on both hemispheres on the surface of Earth, the total albedo on the top of the atmosphere, because of the cloud, they mask everything, and the difference is very minimal.
Right. Okay. So even that fear stories does not stack
up. So the story that you're gonna melt somehow from carbon dioxide, you're gonna melt the ice in the poles, and then this will decrease the albedo, and that will accelerate the warming. All this positive feedback. That I don't think this works in models. That's how the whole thing came from, but it's not in reality. It doesn't work like that in reality.
Which, incidentally, what we're talking about is one of the takeaways from our discovery, that any given planet maintains its own temperature through variation of cloudiness.
Our findings led us to the following conclusion. because in our model that has the long-term temperature being a function only of solar radiation above the atmosphere and total pressure, there is no albedo term in there. There is no variable between the planets. Every planet has a different albedo, right? Say, for example, Venus has an albedo of 90%. 90% of light gets reflected back to space. Earth has an albedo of 29%. Mars has 25%. Moon has only 13.6%. Very different albedos. Yet there is no albedo variation in our basic models for the long-term temperature, and yet they all fall on the same line, right, on the same continuum.
Okay.
Which means that the albedo has kind of two components. One component is the long-term component, which corresponds to the long-term temperature in the climate system, of the planet. And that long-term component is a byproduct. It's not a controller of climate, but it's a result from climate. It's a result of climate, right? It's a byproduct of the climate system itself. So that albedo is the bulk of the albedo of any planet with an atmosphere, right? But then there is a small fraction that is affected by the clouds and how the dynamics of the clouds, and if the clouds, like on Earth, happen to be affected by the magnetic activity of the sun through the change of the flux of cosmic rays, for example, and the change of the rate of nucleation in the atmosphere, and therefore the formation of clouds. If that's the case, then the sun, through this magnetic activity, can impact the cloud cover, and those small fluctuations in the cloud cover can cause the changes on the surface temperature, but those are very small changes compared to the background bone of the temperature that is defined by solar radiation and the pressure. So now our research has led to totally new understanding of the role of albedo in climate. And the role of albedo in climate is that the bulk of the albedo of any planet with atmosphere is actually the result of the climate system itself. It's not a control of climate. Only a small fraction of that albedo that is controlled by the sun magnetically through the cloud cover can have the effect of modulating the annual temperature, decadal temperature around this long-term baseline. So the pressure and solar radiation determine a baseline, but then the fluctuations around the baseline are caused by those changes in cloud cover. You see?
Okay, so the magnetic field or the radiation from the sun, sometimes distance to the sun, some would argue sunspot activity, that is causing the short-term variations. But the actual distance to the sun, which changes on elliptic orbit, and the gas pressure, according to you, that's the primary reason for why the temperature is the way it is.
That's the primary reason that determines the long-term, we call it baseline temperature. The baseline temperature, the variations around the baseline are caused by the cloud albedo changes, but the baseline temperature is defined by the pressure and the distance from the sun.
Okay.
We have concluded that there are two separate drivers of climate depending on the time scale you're looking at. When you're looking at that, like you mentioned, the proxy record, where they infer the temperature changes over thousands to millions of years, right? On that time scale, thousands to millions of years, we hypothesize that it is the changes in the total pressure, because it requires the changes in the global temperature at that time scale are so big, it requires a change in the baseline temperature. In order to change the baseline temperature, you can do only two things. You have to change the distance from the sun, or you have to change the pressure. The orbital models that we have, the most advanced orbital model that we have, which is the best version of the Milankovitch cycles models, if you will, because Milankovitch was in the 1940s. We now have very sophisticated models, and there is a team actually in France. That's all they do. They maintain this model of orbital cycles that is very precise and accurate to plus minus 250 million years. They had equations. They solved that. It's affected also by the movement of other planets in the solar system. So it's the whole thing.
Gravity of Jupiter usually.
All that stuff.
Yeah.
But the bottom line from this model is that the changes in the average annual distance of the Earth from the sun has been minuscule. I mean, I'm talking about minuscule. It can account only maybe for like a 0.1 degree or something change in the global temperature. Nothing. And at the same time, in the geological record, we see huge changes. Like compare, for example, 51 million years ago during the early Eocene, when there was no ice on Earth, the global temperature was like something like 15 to 17 degrees higher than it is today, early Eocene. So the sea level was like 140 meters higher than today. Very different planet, you know. And but yet the sun was was at the same distance as it is now. So we concluded the only way that you can change this baseline temperature so dramatically is if you have a change in actual mass of the atmosphere. So the mass of the atmosphere has been changing, which has been causing the change in the global temperature on this large time scale.
And what would drive the change of the mass of the atmosphere?
Well, that's another whole other conversation. The first thing is to conclude and to provide evidence that this is actually what has been happening. The change in the mass of the atmosphere is the reason for the change in the temperature of the paleo record. The second question, once you establish that, the second question is how those changes are possible. Well, we now know this is not a new theory, but there is a lot of gases coming from the mantle, including nitrogen. There is a lot of nitrogen coming from the mantle. And so at the same time, we have observations from satellites that show that the Earth constantly loses air to space. And right now, the current estimate is like something like 90 tons per day of air being lost to space, right?
Not CO2, though.
Well, it's everything, because of the turbulence and all that, and the magnetic fields, how they suck this air, they found that actually all gases are being, lost, not just the light gases like hydrogen and so forth. So we have the evidence that the atmosphere is being lost to space. It's a small amount. If you use that rate of loss, you could not explain the huge losses that has to happen in the past, right? Like millions of years ago. So we have no idea. There are maybe mechanisms at work that are not manifested right now. They're not working right now, but they worked in the past, right? But the point is that we have evidence that the atmosphere is being lost. We have evidence that the atmosphere is being replenished from the mantle. So the balance of the flux from the mantle and the rate of loss to space at any given time determines the mass of the atmosphere. When you have more loss to space than what's coming from below, the atmosphere starts to thin. The mass of the atmosphere starts to decrease, and therefore the pressure decreases as well. And as the pressure drops, it gets cooler. The other way around, when you have more degassing from the mantle than you have lost to space, the atmosphere mass starts to increase, the pressure increases, and it gets warmer.
Yeah.
And so this is our hypothesis that over millions of years, that this dramatic, huge change that we have observed in the geological record, like I said, like 50 million years ago, there was no ice on Earth, no glaciers, nothing. Average global temperature was 15, 17 degrees higher. Before that, during the dinosaur time, even it was a little bit even warmer, maybe by a degree or two from 50 million years ago. But the interesting thing is, when you look at the geological record, the majority of time since the higher life on Earth evolved, which started like 540 million years ago, the majority of this time until today, the Earth has been much warmer than today. We are now in one of the few periods that, you can call it an ice age because we have ice caps, For millions and millions, hundreds of millions of years, the Earth had no ice caps, or very little, And there are periods of tens of millions of years where there was absolutely no ice on Earth anywhere. There was no snowfall, nothing like that. So most of the time since life evolved on Earth, the Earth has been much warmer than it is today. What we're experiencing now is that today's climate is like an exceptionally cool. It's one of the outliers, if you will. So then we thought, okay, it looks like the pressure is the driver. So how can we verify that this was the case? And what we did is that we created an extension of our model based on, again, on data from NASA, from those planets, where in addition to the global temperature, we derive empirical relationships based on the actual data that gives you the temperature at different latitudes. In addition to the global temperature, you have the equator, you have the 20-degree latitude, then you have the global average, which corresponds to about 38-degree latitude, then you have the 60-degree, 75-degree, and the poles, right? So we had those additional equations derived from the NASA data, and now we said, okay, we're gonna assume the hypothesis now is that the temperature over the last 50 million years, the change in temperature on this time scale of thousands to millions of years has been driven by changes in pressure. What this would imply when you change the pressure, you change the global temperature. Not only that, but you also change the temperature gradient between the poles and the equator. And this temperature gradient, it's known in the paleoclimate as polar amplification. Why it's called polar amplification is because in the entire geological record, when you had colder than average conditions today, like during the ice ages, the temperature gradient was larger. So there was a lot more cooling at the poles than it happened globally or it was on the equator. Similarly, during the early Eocene, some 51 million years ago, the equator to pole temperature gradients were much smaller than at present. That's because the tropics were only about 9 degrees warmer then, while polar temperatures were nearly 38 degrees higher than today. So the polar amplification refers to the observation that in the geological past, temperature variations at the poles have been significantly larger than those near the equator.
That makes intuitively sense, because the heat flux towards the pole would...
Well, it doesn't make intuitive sense immediately because climate models could not reproduce polar amplification. Okay. It just totally fell on that.
My view on models has been, it's a form of modern-day prophecy. If Nostradamus lived today, he would have used a computer model.
The models are a useful tool if you have the right model and it has the right physics in it. But if you have the wrong model and you firmly believe that this is the reality, which is not, then you have a problem because the models will give you wrong results and it will mislead you entirely, what's going on. So the models are a tool. It's like you have a kitchen knife, a sharp kitchen knife. You can kill someone with a kitchen knife, you can cut yourself, or you can use it to prepare your food, right? So it depending how you use it. So it's a tool. But you have to pay attention what kind of model you're using, and you have to be honest with you and with respect to the data if the model is correct or not, and if there is a problem with if you discover the model is not adequately representing processes or something, you have to change the model, abandon the whole model, and start a new model, right? So that's how the science is supposed to work. So, but anyway, so with respect to the paleoclimate, we said, okay, so if the pressure is the driver, then we can use the global temperature, observed global temperature from the geological record, use our original model that relates the global temperature to the pressure of the atmosphere and the solar radiation, assuming solar radiation, the distance from the sun has been the same, which this is what our current science says. And we calculate backwards what would be the change in pressure required to create this observed change in global temperature, right?
Right.
So we calculate the pressure that way. Then we use our extended model with the new pressure calculation and say, what is the implication of those pressure changes now on the temperature of the poles and the equator? So then we calculate using the model, what would be the required change in the temperature of the poles and the equator if the pressure were the driver. Then we use independent data from the proxy record that has the measured temperatures of the poles and the equator, and has the temperature gradient between the pole and equator, and we compare with what the model has predicted. The match is 1-to-1. The polar amplification is predicted very accurately by our model.
I have to ask you the elephant in the room. Do you have fudge factors in your model or anything of this sort?
No, we don't. We use the equation that were derived from planetary data. This is another aspect which is very powerful in science. You use relationships derived from spatial arrangement of planets, like what we observe now, and you apply those relationships over time to study the climate behavior on a one point, which is Earth. So that is a very powerful science argument, because the physical laws that create the spatial pattern of something are the same that determine the temporal pattern of a phenomenon over time.
So to put it in a context that I understand, you have this model that you derive you have the law that you derive from the planets, proving that pressure drives the temperature. It's similar
not proving, but actually discovering that the pressure was the cause for the thermal effect of the atmosphere.
Yeah. Yes. Okay, and then you have an independent data set, which is the proxy record.
Right.
And then the thermal difference between the pole and the equators. And you did not fudge your model. You got the numbers on the independent one, and that gives you confidence in the discovery and in the model.
Because the polar amplification, or the difference between the polar and the equatorial temperature, was something that was totally independent from the geological record. compared to the predictions from our model. There was nothing that the model used to budget against that. And then we compare the model results to independent data, to independent observed data, right? And the match was so good that, so basically the only explanation for the observed polar amplification of geological record has to be change in pressure. Nothing else can account, because climate models that are driven by CO2, if they bump up the CO2 high enough, which they could do, which in some cases they don't have, they have to bump it to a level that's not even supported by the geological data. Say, for example, data said maximum CO2 was like...
It depends on the sensitivity they put in, so, you know...
Well, but sensitivity is something that you know, yes, different models have different sensitivities because of the feedbacks and all that, that they have this mechanisms in there. But during the early Eocene, the CO2 did not exceed 2,500 ppm, according to reconstructed data from the paleo record. Models, in order to reproduce the global average temperature during the Eocene, they require like over 4,000 ppm. So first of all, they require much higher CO2 to produce the global average temperature. But then when they do that, and you compare what's the temperature on the poles and the equator is way too hot, the poles are way too cold compared to the geological record.
Right.
So this graph compares, this is the early Eocene, 51 million years ago. And those dots that you see here, those are proxy-derived temperatures at different latitudes, right?
Right.
And then the dashed blue line is basically kind of the median, the average that goes through those proxies. So on the x-axis, you have the latitude, starting from the equator, 0 latitude to the 90 degree to the pole. And then you have the climate models, which is the gray line. And you see that when you get to the poles, they're actually very away from reality. Because the reality,
they don't predict the Antarctica very well. That's always been a critique against them.
Well, not only Antarctica, also the Arctic. Both poles are problems. This one here is the average between the northern and southern hemisphere. The red line is our model, assuming that the pressure was 2.8 times higher than it is today. The model predicts actually very well. The red line is very close to the dashed line in blue, which is the data, okay?
Yeah.
So it's an illustration how well the model predicts the temperature distribution across the latitudes and how badly the climate models have failed to do so.
So the difference between the pole and the tropics is then, as you say, due to pressure, because the atmosphere's got a different weight.
Yeah, so we found that the only way that our model could predict correctly the changes in the temperature amplitudes between the equator and the pole, the only way is through the change of pressure. And if you don't have that, you could not predict how the equatorial temperature changes with respect to the polar temperature.
It was interesting to know what causes that change in pressure.
It's basically the balance between degassing of the mantle and the rate of loss of atmosphere to space. This graph shows the temperature of the poles and the temperature of the equator for the last 780,000 years. The observed temperature of the equator is the dark red. The red one is the predicted by our model. On the poles, the dark blue is the one derived from the ice cores, and the pink is the one calculated by our model, assuming that pressure was the driver of those changes between ice ages and interglacial periods. You see the match is remarkable. You see a lot smaller variations of the temperature equator and a lot larger variations of the poles. And this matches the observations. And it tells you that variation in pressure has to be the explanation for the ice ages. The reason we had ice ages because we had periods of low pressure, of low atmospheric mass. And the amount that we calculated required, for example, to have the last glacial maximum around here, 21,000 years ago, the pressure was 32% lower than it is today. We had the 32% less atmospheric mass than today.
How would that relate to the Milankovitch cycles then?
Well, this excellent match between observations and the proxy data, there is no Milankovitch cycles in there at all. And there is this myth in the paleoclimate that they say, well, Milankovitch cycles, they have an impact. Milankovitch cycles do not affect the average distance to the sun. In fact, the changes in the average distance to the sun over this hundreds of thousands of years is minuscule.
Well, I'm speculating here now, but I mean, if the argument is the
ultimate
Milankovitch cycles is
language-
caused by the gravity of Jupiter, wouldn't the gravitational constant change given the distances?
Well, nobody talks about that's another whole theory. But you mean changes in the gravity of the Earth to have these fluctuations?
Well,
There is
that's-
there is no evidence for that. Yes, I know that the gravitational constant, the capital G, the Newton's gravitational constant, some people think it's not a constant, and there is empirical data showing that there is some variations, but those variations are very, very small. They're not like huge.
Yeah.
And so that's about theory of gravity. But as far as the science is concerned right now, we assume, and the evidence shows that the gravitational constant is a constant or close to a constant. And so you could not expect variations in the Earth's gravity because on this time scale, not possible. The only feasible mechanism that we have concluded was the changes in the total pressure and the mass of the atmosphere occurring on timescales of tens of thousands of years, which is the reason why we have the ice ages and the interglacial periods.
Have you plotted CO2 next to that? Because it can be that the Earth's CO2, because CO2 lags temperatures in many cases.
Well, the CO2 has a good correlation on the period of the ice age. The CO2 has a very good correlation with temperature, but that's because the temperature is controlling the CO2, and the fact that it's controlling it, it's known from general principles in ecology and ecosystem dynamics. Everybody knows that when you have higher temperature, more CO2 is being emitted from the oceans and from the land through the respiration of ecosystems and so forth. There is a substantial lag that even the IPCC has acknowledged in the relationship between temperature and the CO2 during the ice ages. And this lag is anywhere from 400 to 4,000 years. The CO2 lags temperature by 400 to 4,000 years, which is huge, and therefore eliminates the...
it's rare for the cause to follow the effect,
Yeah, you could not have the CO2 causing, although IPCC trying to...
but with the IPCC, it's just the politics driving the science there. There's no...
The climate models, they without the CO2, they have absolutely no way to simulate the ice ages. The change of the CO2 is being used as a driver in the climate models, in the standard climate models, and that's the main driver that they're able to reproduce more or less the global temperature variations during the ice ages. But then, like I said, they totally fail to reproduce the polar amplification. And this part is kind of they're silent about this. They say, oh, look at this global temperature, the CO2 has a forcing, and here is where without this forcing, we could not reproduce that. And if you include the forcing of CO2, boom, you have a good reproduction of the global temperature. But nobody's talking about the polar amplification because there the models fail 100%. And that tells you that the CO2 is not a driver. It's one of the signs that the CO2 is not a driver. Plus, you have the lag but the models, they say, initially you have a kind of a push from the orbital cycles, and then the feedbacks takes an effect, and so the CO2 in the beginning of the cycle is somehow a consequence of the temperature change, and then it becomes a driver of temperature. It's like, wait a minute, things don't work like that in nature.
Yeah, it's there's a lot to it that doesn't add up. Just to ask you the last two questions I've got, because it's been really instructive. As I say, Ian Holmes and Piers Corbin have said something similar along these lines before. I haven't had time to study exactly what they were saying, but do you agree with them more or less, or
what exactly are you referring to that they said something?
So I know Ian Holmes came out in 2019. He published a paper saying that the greenhouse effect doesn't exist. He referenced your work for what it's worth.
Yeah.
And then he said it's driven by the molar mass, the temperatures.
Yeah, Holmes. Yes, I have actually interacted with him, and I think I sent him an email when his paper came out. He uses the gas law.
Yeah.
But then what he does, he made a mistake that he thinks that the density of the air is a driver of temperature, and that's not the case, because the density of the air is always the result in the atmosphere, at least in the context of the atmosphere. It's always the result of temperature and pressure. Okay,
right.
That's how the chain of causation works. So in his paper, he yes, he argues that everything can be explained by the gas law, but in the gas law, you have basically one equation with two unknowns. So the unknowns are temperature and volume, right? Or temperature and density, you can say, okay? Well, in order to solve, the equation correctly, if you have two unknowns, you need two equations. You could not use one equation. His mistake was that he used one equation, and he used the gas law to calculate the temperature from the gas law, assuming that pressure and density are the drivers. Well, pressure is the driver, but density is not the driver.
Because density is anyway related to pressure. So
well, the density is a result of pressure and temperature. It's not a driver of temperature. It's a consequence, right? So that was his mistake. The overall his concept was that the radiative greenhouse effect does not exist, which is our conclusion as well. So in that regard, we are the same. But the way he tried to explain this has a serious problem. In our case, we analyzed data from the planets to come up with a new relationship that was unknown before on a planetary level that relates the relative thermal effect of the atmosphere, which is defined as a ratio of current temperature of the planet to the temperature without atmosphere, right, of the planet. It's a dimensionless ratio. And this ratio was related empirically to the pressure with a very high accuracy with this curve that we have derived.
Well, by the way, one critique I read against your work, because I was reading the critique as well, was they say that you were just fitting curves. There was a critique on WhatsApp with that.
Yeah.
You were just playing with coefficients and fitting curves.
I've heard this many times before, and the simple truth is that the physical laws that we call laws and nobody doubts them, like the ideal gas law. Ideal gas law has the ideal gas constant in there. Well, that's the best example of a parameter that has been fitted, because the ideal gas constant is a fitting parameter. It's based on measurements. It's not derived from theory. Or at the bottom of the physical theory that we have is actually empirical measurements. So the first constant, look at the Planck's constant. Planck's constant is also based on measurements. Yes. So the very fundamental constants that we have, they are based on measurements, and then from those constants we have the derivation of other constants. So the physical laws that we have, they have the roots in the actual measurement. So we have.
Have you taken an independent planet and see if it works as well?
We looked at Pluto, we looked at Europa, we looked at Callisto, and this is discussed in our paper.
Yeah.
And the predictions that were done with for those planets that were not part of the of the regression analysis, they were very close to what actually is observed. To the point
that sort of argues the point, because I mean I don't think, because when I read the critique, I don't think they read your paper, or they didn't understand it very well.
No, they don't. A lot of people just.
I've dealt with a lot of scare story scientism stuff on this channel, and a lot of people don't critique necessarily what is said, but what they think is being said. One reason for that is this. It's very traumatic for people. One book that inspired me as a student was Thomas Kuhn's Theory of Scientific Revolutions, and how paradigm changes occur. And whenever I deal with these type of issues, it is very traumatic. Okay, psychologists has proven it, for people to change their minds, especially when they've been sucked so emotionally into an issue. And that's one reason. There's a reflex reaction to not changing your mind. I've seen it with COVID. I've seen it with other disease stuff. I've seen it with climate. I've seen it with other issues I've been into. The first time you change your mind on a typical topic, it's traumatic. Okay, so if you asked me this, gave me this 3 years ago, I would have said you're nuts. Okay, but because I've been through the process so many times, I said, okay, this is just another one. Let's slowly guide into it. And I'm keeping an open mind, if I put it at the moment, because I've heard these rumors on the internet before of your work. I haven't really dug into it. And even if it ends up being wrong in the future, you end up with a much broader understanding of how things work. That's always the point of scientific discoveries.
This curve here is the empirical curve that we derived. Notice on the vertical axis, you have the relative atmospheric thermal effect. We call it a rate. And that's simply the ratio of the current global temperature of a planet measured, divided by the temperature of the planet without atmosphere. And we have a
Right,
way to calculate this, and the formula that calculates this is in our 2014 paper. So, and this formula has been verified against temperature of the moon, so it is accurate. This ratio is the relative atmospheric thermal effect, and as you can see, across all these planets, from Venus to...
So I just want to understand how you took it. You took measurement from all those planets, and then...
yeah, measurements were provided by NASA in terms of global surface temperatures. The no atmosphere temperature, TISA BNA, the one that we calculated from our model, the model was verified against data from the moon, also from NASA.
And on that curve, did you look at another planet in the solar system that falls onto that curve?
Yes, the planets that are available that we checked our model against, they basically have very close to zero pressure. They're around here, they're around the moon, right? But they are different distances from the sun. They have a little bit of pressure, like Pluto has about
to make it more interesting, I would say if you take another few planets and you add it onto that curve, just to show where you measured. You don't have to show you, obviously.
The problem is we don't have that many planets in the solar system, right, to choose from. The ones that we picked here for the ratio analysis, now Titan was independent. It has a good atmosphere, has a pressure 50% higher than on Earth, and it's very far from the sun. The radiation reaching Titan is about 1,000 times less than what is on the Earth. And Titan was not included in this regression analysis, yet Titan is very close to the curve. You can see that this independent point right here.
Yeah. And
Titan has some uncertainties with their data, so because it takes like 25 years for Titan to make a full circle around the sun. 1 year on Titan is 25 years on Earth. And the measurement that we have that are taken on Titan, they span a period of about 10 years or so. So it's not a full circle, you see, around the sun. So there was some uncertainty with the data, but still the error was about 1.4 degrees Celsius in the calculation of global temperature from our model that was independently derived.
I mean, this is a very useful curve on its own to get the temperature of a planet far away.
Yeah.
I mean, the principle is actually what I'm more interested in sometimes than the curve and the model.
The interesting thing about this curve is that it's very similar. The shape of this curve, the way it goes, like this, starting, increasing rapidly at low pressures and then, leveling off. This nonlinear curve is very similar to other temperature-pressure relationships in different systems that have nothing to do with the planetary. The numerical expression of those other curves is very different, but the shape is very similar. So here is 3 different systems. On the very left, you have our relationship derived from the planet. This is our model, and here's the numerical expression of that. In the middle, you have the what's called the adiabatic change of temperature as a result of pressure. This is called the Poisson relation, or Poisson formula. Yeah. This applies to our atmosphere in the vertical sense. When you go from the surface to the higher levels of the atmosphere, the temperature drops along very close to this curve. Not exactly, but it's close to that. And this is the result of the temperature dependence on pressure. So you have 2 pressures here, the ratio of 2 pressures and the ratios of 2 temperatures. T0 and P0 are the temperature and pressure on the surface, and then T and P are the temperature and pressure at the level, higher up in the atmosphere. So you can see that this is a pressure-temperature relationship in the atmosphere, theoretically derived from the ideal gas law and the first law of thermodynamics, the adiabatic form of the first law of thermodynamics. It's a very simple derivation.
Isn't it similar to Boyle's law, if I remember now correctly?
Well, the Boyle's law and Charles' law and all those are part of the ideal gas law. There are different aspects of that. We can talk about this, but that's a different conversation. Anyways, compare the shape of the curve on the left and also the curve in the middle, and you can see how similar it is. This is a typical pressure-temperature relationship curve.
Yeah.
Numerically, they're very different because they're different systems, but the shape of it is similar. The curve on the right, it's very interesting because that's the Stefan Boltzmann Law expressed in terms of pressures. Now, very few people, even scientists sometimes don't realize that radiation has pressure to it. Why? Yeah. Because watts per square meter as a unit, watts per square meter, this is the unit that they measure radiation, basically means the product of pressure times the speed of light.
Yeah, because the photon is mass, right?
Yeah, so pressure, so radiation has pressure. It's a measurable amount. In fact, the Japanese, they had a satellite that went to the sun or close to the sun that was fueled by the pressure of solar radiation. That was the only propulsion system. You see, so pressure is very measurable quantity, and around the Earth that you have those gazillions of satellites. After a certain period of time, they have to adjust their orbits because the pressure from the sunlight is pushing them off orbit.
So the pressure here in the regards, it's the mass of the photon over the surface of the Earth or the whatever atmosphere.
The funny thing is that the radiation has pressure. It's in the theory, it's measured also, but at the same time, the photon is supposed to have no mass. The photons have no mass, but at the same time, they have momentum. Momentum is the product of mass times the velocity. Yeah. So it's a very funny thing, and I think it's a little bit of a contradiction, but that's what the standard physics says, that photons are massless, yet the radiation flux has pressure, which implies that there's mass involved, right? And we don't quite understand, I guess, how this thing works, but that's what the physical theory is. In this regard, the point is that you can express the Stefan Boson Law here, that's given in yellow. R equals sigma is the Stefan Boson constant times the temperature, absolute temperature to the power of 4. You can express this in terms of pressure because radiation is basically the product of pressure by the radiation times the speed of light. And you can use the temperature ratio. You can use the irreducible temperature of a deep space, which is about 2.7 degree Kelvin. 2.75 degree Kelvin. This is based on the background radiation in space, right? So the Stefan Boson law can be expressed in terms of temperature ratio and pressure ratio, and you have this curve, which is very similar to the curve on the very left here across the planets. Numerically, again, don't look at the absolute values of the x-axis and y-axis; they're very different. But the shape of the curve is very similar. Again, this is pressure-temperature curve.
Yeah.
And this slide basically gives, like I said here on the bottom of the slide, the striking similarity of responses between the new planetary temperature model that we have derived and other well-known pressure-temperature system gives credence to the notion that our empirical model describes a macro-level physical reality. In other words, what you're seeing here on the very left is a macro-level physical law. We think it's a law because the accuracy of this could not be, this is not an accident.
I mean,
so this is the answer to people that say, oh, it's just a curve fitting, it doesn't mean anything. You could not achieve any curve fitting of this type using the radiative greenhouse theory, because once you introduce the composition of the atmosphere, all relationships across planets, they fall apart. There's no continuum. There's no continuum.
Yeah, I say I don't think they've read all of the theory. I mean, what would be interesting, a good way to present it would be to plot the Stefan Boltzmann law against the other one and to see, to show them this. So this plot is a very good example of that. I mean, I'm curious to know why the coefficients would be the way they are.
Well, because it's a different system. It's a whole different thing. Here, for example, the radiation is the pressure is measured in micropascals. Which is micro is a 1 millionth of a pascal. Here on the planetary level for the atmosphere, you have pressures that are measured in kilopascals. I mean, a very different system,
Yeah, so these are system coefficients, if you can call it that.
Yeah, they're absolutely different, yeah. But the similarity is in the overall shape of the curve. That's what is important.
Okay, that's very interesting.
Yeah, what I wanted to say before is the major, and Ned alluded to it, the major criticism that we've had is we don't have enough data points. But my answer to that is, take the law of gravity, go on the top of the Eiffel Tower or whatever, or Pisa, and throw the rock and measure distance and time, and take 4 measurements, and then draw a curve through that, and you're going to come up with the 9.8, whatever the number is.
9.81,
Acceleration.
Yeah, you're going to come up with that number. And the correlation coefficient is going to be very, very tight. You can do that with 3 or 4 data points, right? So we have 6 data points. What's amazing is not the fact that we don't have enough data points, but the correlation. It's like 0. A couple of 9s and an 8.
And also, you cannot just create a planet in the solar system.
We are limited by what's available in the solar system. Well, the other thing is that we have excluded all the planets that are gaseous planets, but we need planets that have hard surfaces because we're talking about the atmospheric effect on the surface. So you could not consider Jupiter or Saturn we don't know if they have any surfaces. Nobody knows, but they are assumed to be gaseous planets, so they have no surface, right? And so those planets are excluded because, first of all, we don't have any data deep down. What's the pressure and what's the temperature and all that. We can only speculate. There's no.
What about the asteroids in the solar system? Would that be possible?
Which one? The asteroid? Well, they are basically airless.
Airless.
They don't have any atmosphere. The asteroids are, they are just rocks, right? And we have tested our model actually with planetary bodies with moons that are close to that. They have a little bit of atmosphere, like I said, Pluto, Europa, Callisto.
The fact that we hit that number within a degree or so, that's unbelievable. To me, that
is. I mean, what is important in my takeaway is this: look, whether you hit the correlation of 0.1, or whether it's a 1 or a 0.9 or 0.8, even you showed to me the concept, that it is a pressure system, right?
Yeah.
This is the important takeaway from this. We can debate the meaning of the coefficients. It's a system coefficient. This is what I would say. But it works. It works analogous to a piston.
Yeah. The other criticism, by the way, is that we have 4 constants.
Yeah.
That's
regression coefficients. Yeah.
Yeah. That's another. But that's really not the point. We have an equation that fits, and we have predictive capability.
Yeah.
This equation is an exponential form. It can only fit exponential relationships. This is not if you try, and I have done the exercise, if you use a polynomial, the polynomial is something that, you can use the 4th order polynomial, which will have, again, 4 regression coefficients.
Story.
Yeah. But the polynomial, it kind of goes through, it can go through all the points, no problem. But then between the points, you have this wiggling, like a snake, which means no physical sense. You can't have that, right?
Yeah.
So the only function that fits those 6 points in a physically feasible and realistic manner is this exponential curve, and this exponential curve is very limited to the type of data it could fit. It doesn't fit any random points of 4 points. You could not do that. Only the polynomial can fit any random points. This is a high-level relationship that is not directly derivable from the gas law. It has an explanation, theoretical explanation in the thermodynamics in the gas law. You can refer to that. But it's not directly derivable from that. You can not get a piece of paper on the gas law and some other equations and derive this. Why? Because in this curve, you have the effect of clouds. Like I said, the bulk of the albedo of any planet with atmosphere is the result of the climate system. It's not a driver of climate, but it's a consequence of the climate system. So as the pressure increases normally, you have increase also in the cloud cover. For example, look at the internal planets like Mars, Earth, and Venus, right? Mars almost has no clouds. The albedo of Mars is mostly because of the dust in the atmosphere, but it has a 25% albedo, so it's less than another word, but has no clouds. Earth has more clouds because it has water vapor. Venus is totally covered with clouds, 100%. Yeah. And those clouds are permanent. You could never see the surface of Venus from the top, because they're very thick. So there is some kind of a qualitative relationship as the pressure increases. And again, Mars is the smallest pressure, Earth is in between, and Venus has the highest pressure. As the thickness of the atmosphere increases, or the pressure of the atmosphere increases, you have a tendency to create more clouds. Okay.
Is that because, after a certain amount of pressure, just the gases start convecting more?
Well, those are many thousands of processes involved. You could not pinpoint to one thing, but this is the net result. And because of that, this curve that we have derived, it has implicitly the effect of clouds in there, right? The formation of clouds as you increase the pressure. And so this is why it's a high-level relationship that you could not derive from low-level processes very easily. But this kind of a curve can serve to constrain the climate model, say, okay, if you're going to change the pressure on another planet, you're going to apply the model, this is what you're supposed to get. Yeah. If you apply the climate model that works with, small-scale process and aggregate things up, if the model doesn't come to this level, that means the model, there is something, a mistake in this aggregation. There is something, but it's very difficult to derive this curve from the component processes, from the processes that are inside the system.
It's a big system analysis, and it's sort of, it sets the parameters of what can happen inside of the system.
Yes, correct.
Yeah, it's very interesting. I mean, I've learned a lot from you too. Can you just maybe explain for those? Because Al Gore has got movies around of skits with greenhouses saying how simple it is. So, what would the net Nikolov-Karl-Zeller one look? It would be a car piston of something and say this is how it works.
Well, just one word is completely wrong. So Al Gore, he's not even a scientist. It's just wrong,
Yeah.
If you have to explain more, then you have to go in details why it's wrong and how it's wrong and all the discussion we had up to this point. But it's a cartoon, he has a cartoon. He doesn't understand any science, and he just regurgitates what he was told by other scientists.
He knows how to make money out of causes, but yeah.
It's the same thing like Bill Gates. Bill Gates is the same situation. He actually he paid professors, scientists, climate scientists, he said actually in an interview, for years, maybe 10 years or something, to come to his house and lecture him, tell him how the climate works and all that. But he himself has no basis of thinking because he doesn't know physics. He never graduated from college. He could not say, okay, wait a minute, this doesn't make sense, or how this works. He could not ask any questions. He can only suck whatever comes from the professors and regurgitate that and thinks that he understands something.
It's not just him, and politicians they feel a little bit insecure about their lack of understanding, and they love a simplistic explanation. I mean, I'm not sure how much of my audience is going to follow what we said tonight, with all respect to them. I mean, I've covered politics that most people intuitively follow, but this is complicated stuff, They say the best analogy I can say is the greenhouse effect is not a blanket. It is a car's piston. But obviously you'll have to understand how a piston works, right?
Yeah. So basically the bottom line is that the greenhouse effect, which is the foundation of all climate projections that we currently have, it is not a radiative phenomena as has been taught for well over 100 years, 120, 150 years. It is a pressure phenomenon. It is a form of compression heating. People that, engineers, especially when I say compression heating, everybody says, oh yeah, well, the piston in a diesel engine works to compression. It's a similar analogous mechanism. The only place where the analogy breaks is that in the atmosphere, we have a kind of the surface, we have a constant pressure. It's not like pumping, there's a small pressure variations, but they're very small compared to the overall pressure. But this constant pressure creates a constant thermal enhancement. That's the part that many, including many scientists and many people don't understand. They think that you have to have this pumping effect all the time in order to get the higher temperature. If you don't have pumping, no, it doesn't work.
Because one guy said to me the critique has been that when you compress gas, eventually it cools down. Yeah,
well, it cools down in a tire or something, or on a pump that you have small system that's surrounded by a big system. You have convection, conduction going on. When you have a big planet like this is a huge system, and the surface of the planet is completely under compression. There is not a single square inch on the surface that there's no compression, because the air is everywhere, right? It engulfs the entire surface. So we're talking about the surface temperature here, right? So, like I said, the lapse rate in the atmosphere, which is a decrease of temperature with elevation, very well known in atmospheric thermodynamics that this is the result of a decrease of pressure with height. I derived those equations in my video. The point is that the greenhouse effect is not a radiative phenomena. The thermal effect of the atmosphere is real. When we say the greenhouse effect is not real, we're referring to what not being real is the radiative explanation of it. That's not real, okay? But the thermal effect of the atmosphere is real. Not only that, but it's 2.7 times higher than we originally thought. It's not 33 degrees, but it's about 90 degrees. If you take Earth with the same pressure and you move it to the orbit of Titan, which is very far from the sun, this 90 degree will not be 90 degree anymore. It will be something like 30 degrees. Because it's so far away from the sun, right? If you move Earth close to the orbit of Venus, much closer to the sun, this 90 degree will become 150 degrees because the sun is much stronger. But the relative effect, 1.46 or 46%, 45% enhancement, it's only depending on pressure, and it will stay both if the Earth is at Titan's position or at Venus' position. It's always a 45% amplification.
So what does infrared absorption then do to the Earth's theory, according to you? Because I mean, obviously, gas is. I mean, from NASA,
Yes.
They
Yeah.
measure obviously infrared absorption, and that's said to be
Yeah.
greenhouse effect. So, what does
Yeah.
that fit in?
So in the climate science, the entire attention is to the long wave radiation. What our research has shown is that this is barking the wrong tree. Why?
Yeah.
Because the long wave radiation is a byproduct of the operation of the climate system. It's not a driver. You have to focus on the effect of the solar activity on clouds and cloud albedo, because the changes in the cloud albedo are causing the variation of the radiation reaching the surface, and therefore small changes in the global temperature and the global climate. This is what we observe as climate change over the last 40 years, and in fact over the last 150 years. That is the whole thing.
Yeah.
So instead of focusing on that, they're focusing on some imaginary things. Well, they're not imaginary. The long wave radiation is real, but that's not the driver. And you could never understand that. The cause and effect has been mixed here. They're mixed up. They're reversed in the climate theory. You could not see that till you have this discovery like what we found, this relationship between pressure and temperature across the planets.
I like to, when I talk about this with somebody different, I like to talk about, one, that the business the gas laws, and how the molecules in the gas laws do not distinguish between carbon dioxide and oxygen, like I started talking, make a point about that. And the other thing I like to call attention to is the Copernicus relationship. Or here we are, the human mass of people, and we're looking out, and it's obvious that the sun rises and the sun sets, so it's obvious the sun's going around the Earth. There's no doubt. It's absolutely obvious. And if you say it's not true, there's something wrong with you. Today, it's obvious. The carbon dioxide's going up, and it's been getting a little warmer. That's obvious. There's no, and here's some explanations. However, what did Copernicus do? He took a perspective from the solar system looking in, right? He's actually, why is Mars going backwards, right? Regressing. Oh, if we look at it from this perspective, boom. And that's what Ned and I have here. We're looking at the solar system from the perspective of outside in. And all of a sudden, there's a whole different picture. And that whole different picture is so simple. It's a lot simpler than the climate models. Very much simpler.
They have those infamous, I call them infamous because they are kind of ridiculous, positive feedbacks in the climate system that amplify the warming effect of CO2.
Yeah, the analogy is the equations that it took to make Mars regress and then go forward again. It's the same thing, just a couple hundred years later.
No, I mean, the water vapor feedback, in any ways, that function is not well defined.
Of course there's a water vapor feedback, but that's at a much different scale. That's down here in weather forecasting.
No, but anyways, the future prediction on water vapor alone makes no sense to me, because first of all, more water vapor means you might have more rain, more clouds. So it can work either way. To assume it's only positive.
Wait a minute.
Water vapor feedback in the climate models, into the theory, it is totally fictitious thing, and it's based on purely on the theory that when you have more water vapor, more absorption will happen of long wave radiation. So therefore, the warming will increase, and that's how it works. But nothing like this happens, because the water vapor, the only thing it does, in order to have water vapor and clouds up there, there has to be a cooling on the surface, because this water vapor, when it evaporates from the surface, this is where all the water vapor comes from the surface. It will cause cooling, of the place where it evaporates, because water vapor has an enormous amount of heat capacity, and it's called the heat of vaporization. It's a large number, so it takes a lot of energy to evaporate water from the surface to the atmosphere, and then it goes to some height, it reaches the condensation point, and it condenses, and it releases that heat up there in the atmosphere. So what the water vapor does, it transports heat from one location to another. It doesn't create new heat in the system. It doesn't create additional heat. It just transports from one place to another.
So the positive feedback, but look, there's a lot to it that doesn't add up.
The positive feedback from the water vapor is being used in this concept called the runaway greenhouse. Runaway greenhouse is when you have a certain amount of solar radiation heating the planet. This is causing the water to evaporate from the surface, the water then causes additional warming to this trapping of long wave radiation that causes more water to be evaporated, which causes even more radiation to be trapped. It's a classic example of the violation of the energy conservation law in perpetuity. It's like never ends, and it gets to a point where all the oceans evaporate, at some point by itself, on autopilot.
And it never rains.
It makes no physical sense. I mean, the runaway greenhouse effect is such a vivid example of direct, gross violation of the first law of thermodynamics.
Let me ask you one question. Based on what you've heard us talk about, and you just brought up water vapor, hypothetically, what if all of a sudden we had no more water vapor, no more water on planet Earth, but we had the same pressure on the surface, and it was all 100%? Two scenarios. The same mix of oxygen and nitrogen and carbon dioxide is one scenario. The other scenario is 100% carbon dioxide.
Well,
what would the mean surface temperature be in those scenarios?
More or less the same. The atmosphere might just be higher or lower,
So you've just told me you got what we're talking about. Thank you.
Yeah. The temperature is the same, but the critiques of our concept will say, oh, wait a minute, if you don't have water vapor, you won't have clouds. That means the albedo will be much lower. How come?
That's how the thinking goes.
They are not. But they're starting from the back end of the theory. So I've got then the question here. I mean, any scientific theory must be refutable, right? They must be able to prove it wrong. So how would you prove this theory wrong, I guess?
Well, so first of all, it's not a theory, because a theory is like something like the greenhouse theory that came to the people's mind in their thinking. They have limited amount of information. They construct a mental picture how things work. And they say, okay, this is our theory. So now we go and find data and see if what we think is happening is actually occurring in reality when we do the measurements, right? In our case, our curve and this new idea about what a thermal effect is, that is a pressure phenomenon, comes directly from the data. We didn't have this in our minds first and then try to find the data. We looked at the data, we analyzed the data objectively using dimensional analysis, and this came out. So in that sense, it's not a theory. It's a discovery. It's a discovery of a mechanism which is real because it comes from real data. Okay.
Right.
There's no question about it. Now, the thermodynamic theory that exists, in physics, can be used to explain this relationship that we have discovered empirically. Right. So here we're going the other way around. A theory that needs to be proven, but it's a relationship that's a fact that needs an explanation based on what we know about how the system works.
And the only explanation thus far is, unless there's a better explanation. But the fact is the relationship holds.
Come up with a better explanation, or prove that NASA screwed up when they made the measurements.
Yeah.
Well, that sometimes happens. You should not.
If you read our paper and look at the abstract, you'll see all the work that was put into Mars, and we've had a lot of criticism about Mars, but there's a whole section on how we came up with the Mars number, because Mars has many different elevations.
The funny thing about Mars is that there is now so many measurements of Mars. There's so much data about anything about it. But when you talk to people that are working with Mars, NASA people, the last thing they're interested in is about average temperature of Mars. Nobody cares about that. It's like it's not.
I mean, we have another planet, right? So that's at least an independent data set. So nobody changed the CO2 on Mars, as far as I know. So that should be a clue as to why this works.
Same with Venus.
Or Venus, or
Same with Venus.
About 95% CO2 concentration-wise.
Yeah. I guess the last question here, like, how have you been treated by the community and the people around you?
Why do we have alternative names? Den Velokin and Lark.
You published on a false name. What's the story behind that?
There is an article in the Washington Post, and then there's a blog article that I posted my answers to the reporter's question from the Washington Post. But basically, by that time in 2011, we had a poster that we presented on an international climate conference here in Denver, in Colorado. We had a poster and there was so many people coming and interested. This was like preliminary results from what we have now. I mean, the concept has not changed, but the data were not quite refined and the equations were not quite refined. So there was a, the numerical part of that was not the same what we have now. But the concept, the idea was over there already, because we have discovered this relationship even with the preliminary data that we had. So we had a poster. It was the very beginning of our research. No papers published, nothing. And I remember at that time there were so many people coming, being interested in this new concept. I lost my voice. I was like, it's kind of noisy. You have to raise your voice to explain people to hear it. So there were so many people coming that at some point I talked like for 3 hours straight, and then I totally lost my voice. Yeah. Every new person comes, you have to explain, right? So this poster then was picked up by a climate skeptics blog. And then we started working on papers. And the first paper was this business about the size of the greenhouse effect, that is 90 degree, not 33 degree. It was a long paper, 22 pages. So we submitted with our names to journals and all that. And the reviewers.
Let me interrupt right here. The problem was Ned started blogging back, so we became famous.
So we kind of become known. So they see a paper that they never seen before. This is something, whoa, it's not 33 degrees, it's 90 degrees. Wow. I mean, everything is documented in the paper very well, with equations and math and the moon temperature data of NASA. And but then the reviewers, they see something unusual, they immediately Google the names, right? And that's the other thing, that in the peer review, most journals, now there are journals that actually apply this, called the double-blind review, which means they would hide the author's names to the reviewers. Normally, the reviewers can see the author's name, but we could not see their names. We don't know who the reviewers are. They are anonymous to us, but we're not anonymous to them. And so what happens that they see this unusual paper or something, and they immediately Google our names, and they get to this, this blog and talks about this, the whole greenhouse effect is wrong and blah, blah, blah. Oh, come on, you cannot have that. And then you start getting those negative reviews. They were criticizing us about things that are not even in the paper. They're not even
it's the weirdest thing to me. There's two areas where it's like this. The one is cancer research, okay, and the other one is climate, where if you just dare to publish anything, even if it's remotely critical, you get attacked by by witches, like witch burners.
Yeah. So we got to a point that I said to Carl, I said, we could not publish, we could not have reviewers to have objective look at our paper and focus on what the paper talks about. In this first paper, we're not talking about the greenhouse effect is wrong, and we just had a analysis that the greenhouse effect is not 33 degrees, 90 degrees. That's a revelation.
The airless.
We want the reviewers to focus on that and say how we can do that. Well, we got to change our names, because if they Google, something different names, they could not find anything. They have to focus on the content of the paper. So but we wanted to have names that actually would be easily related to us in the future.
That you would remember.
And that's why we decided to spell them backwards. So some people say, "Are you so stupid? Why came up with those? It's so easy to decipher." Well, the reviewers did not decipher it, number one. Number two, we wanted to be decipherable. We wanted the names to be, easily proven that it's us, in the future. That's what we wanted. And so we came with something like this, and, my names happen to spell ideally exactly like a Russian name without changes. Karl's name, Karl, if you spell Karl backwards, kind of doesn't work. So that's why he became Lark.
Lark, release, whatever.
but Relais is basically, it's backwards spelling of Zeller, right?
It is. Well, what language that would be, I'm not sure, but.
Well, I don't know. Relais, I think I found it maybe a Jews, but then Volokhin is a pure Russian name. Actually, it's
Volokhin is. I wouldn't have noticed anything.
So I got congratulated on the Relaz. Small r, small e, capital L, L-E-Z.
It's childish
but
in a way.
It worked. So this trick with the name spelled backwards worked twice.
Okay.
The first paper was the one that 2014. Then we had a version of the paper, the 2017 paper, but it was earlier version. That we talked about this new relationship, and it was accepted in a mainstream journal, accepted, and it was about to be published. They had a preprint on the website, and somebody saw that, and they start discussing this and that, and then somebody says, "Wait a minute, we have seen this idea somewhere else. And one of the so-called climate deniers or climate skeptics on a WhatsApp blog, his name is Eschenbach. I want to mention the name. He wrote a letter. He found out. He said, "Wait a minute, is this like Nikolov Zeller?" And then, oh yeah, the names are spelled backwards. Oh, look at this. He wrote the letter to the editor and alerted him that our names are not the real names that we had in the paper. Although the paper went through peer review and it was accepted, or it was about to be published. So there was a whole discussion after that, that took about 2 months. And the Elsevier decided to, they offered me, said, okay, we have to pull, it was unethical, blah, blah. I said, but it has nothing to do with the science. Yeah, well, that's right, the science, I went through peer review. I said, then what's the problem? Well, we cannot allow this, it was not right.
Why didn't they just change the name and then publish? Get your original name.
I don't know. And so, they figured out that the subject is touchy because this business of thermal effect being 90 degree, it kind of goes to the heart of the greenhouse theory and says that something is wrong. Something is wrong.
No, this is the second paper, Ned. This is the planet paper.
Yeah, this is the planet paper. Paper. Well, the planet paper was very damaging because it basically shows that the thermal effect is due to pressure. There is no composition, nothing. So this could not fly.
Then they allowed us to resubmit it with our real names, and it was accepted. There were 4 reviewers. 3 said publish. 1 said you can't publish because it does not uphold the greenhouse gas theory.
The only thing I managed to get with the editor that they decided to withdraw the paper, I said, okay, they're going to put writing there on the website that the paper has been withdrawn by mutual agreements between the author. Well, I said, I want a sentence there that says, and the withdrawal is not related to the scientific merit of the paper. And he agreed. He says, yes, nothing to do with that. So he put that sentence in there. So now people, when they go and see this paper that was withdrawn, they say, oh, there's something wrong with the paper. Well, look what it says here. Nothing to do with the scientific merit of the paper.
Well, my view on peer review has been we need to get rid of it. I think the great thing about the scientific method is you get to make up your own mind, right? That's the point of thinking for yourself. So if somebody goes through this paper and they come at the end to the conclusion that you two are 2 nutcases and this is just quackery, great for them. That's the point about the scientific theory, that you don't have to agree with everyone. Yeah. But the unfortunate thing of peer review is it acts as a monopoly on knowledge. And eventually it tends towards consensus if you take the game theory to its logical conclusion. So you cannot disagree with it. Yeah.
Well, the funny fact is that the greatest advancement of physics, like talking about general relativity maybe, or Planck function about radiation, relating radiation temperature, it happened in an era where peer review was not established. Yeah, there was some peer review, but it was nothing like that today. And in fact, Einstein, who has published 130 papers, only 1 or 2 papers had actually gone through peer review. And one of the cases, there is a record that the editor said, well, I sent this paper to so-and-so for opinion. Einstein got furious. He wrote me what he says, I sent you this paper in confidence. How dare you to show it to somebody else? So, and yet we have here, the foundations of modern physics actually was done without any peer review. The peer review happened kind of after the publication when people do experiments and they try and they see that this is real or not real, and that's how it should work. You're absolutely right. Right now, in the current system, the peer review works as a showstopper. Yeah. It basically is a filter where you could not publish anything that nobody has heard of before. If something totally new,
it's like the Council of Nicaea in the Middle Ages, after when Constantine created the Council of Nicaea. If you dared to disagree with that interpretation of the Bible, you were a heretic. We're at the exact same times, and the scientists who defend peer review cannot see the irony. Science is supposed to be the antithesis of of religion.
So the peer review is being exaggerated also in a sense. Some people are not in science, they don't know that. Well, it says, oh, this paper hasn't, you've seen this probably with COVID, some new findings. Well, but it hasn't been gone through peer review. So, maybe it's not real, maybe. You may have a paper like with 15 authors, right? The peer review normally involves 2 or 3 reviewers, most of the time 2.
Yeah.
And what we found with our papers trying to publish those things, we run into one reviewer 3 times. The same damn guy 3 times. Why? Because to do a peer review, it's a free service. They don't pay the reviewers, right? So, and normally the people that are doing the peer reviews are younger people. They're younger scientists. First of all, they don't have all this experience. But the older people that are already established scientists, they don't have the time. It's time-consuming to review the paper. They normally decline. They have their careers already on good path. Maybe they're close to their retirement. They don't care about spend time to review other papers. I mean, maybe they do occasionally, but it's not. It's mostly young people. So, and the scope of reviewers that you have is very limited. And if you do a review in one journal, say in some like Elsevier, some of the journals of Elsevier, this gets into their system, and all the other papers of the similar thing, they send it to the same people, asking for review again. I mean, I had my own experience with that. You review one paper in remote sensing, and every week I get an invitation for reviewing things that I don't even have any expertise in, because you're on the list of their reviewers. They're just looking for somebody to review the paper, right?
But it becomes a reputation thing, you know, more than a scientific thing. I mean, I don't read peer-reviewed stuff because some of the journals ask me to buy the articles, and I just don't care. I don't have. And then, you know, it's sometimes arcane fields where, I mean, take even planetary science. Yes, there's a lot of interest in it, but I don't think there's a lot of people that can review it. So eventually the gatekeepers become friends of friends, and that becomes a consensus factory.
That's exactly what happens with the mainstream climate science. They review papers each other. They give awards to each other. You know, so it's a kind of a small circle. And we have experiences, like I said, you know, the number of reviewers that they have in those different, you can look at different journals across, you know, different publishers, but you run into the same people, more or less, you know, the number. And then if you have a paper that is authored by, like, you know, more than 2 authors, for example, it's not our case, but, you know, I'm talking in principle, why you need another 2, if you have a paper of 15 authors and you have 2 external reviewers and they have to say whether the paper will be published or not. You already have 15 authors in there, right? They're more than the peer reviewer, the peers that are reviewing the paper.
I mean, I would get rid of the whole system if it was me, or just at least limit it to some fields. I don't know. I mean, I would rethink the incentive structure of peer review. That is at the heart of scientific regress at the moment. Because, I mean, if you take the period from the 1900s, say, to the 1950s, there was no real peer review. And yet that's when most of the great scientific discoveries occurred.
Right.
Sure. Or even a little bit before that, you know. So it's something serious to think about. And then just in terms of public education, because I think one thing that lacks here is a lot of this debate about climate science is science against authority. It's the same is true of COVID. Right. And I think if the public starts reading open blogs and stuff of this sort, you get a much better public education. And then they will not be easily conned when somebody comes with a new disease, for example, where the death rate doesn't justify the measures.
Yeah. So I think you need some form of peer review, but it has to be limited to detecting gross errors. Say you have a, you know, like
mathematical error.
You have equations, you have some derivation, you have some, and just to see that something doesn't add up mathematically. But anything related to new conclusions, new findings, and rejecting the paper simply because nobody has heard about those things before, that should be not a reason for rejecting a paper. Only when you have gross errors in the analysis or in the data that are being shown in the paper or something like that, then you can say, you know, it needs to be revised. Otherwise, new concept and everything has to be published, because when you have more ideas like that coming in, new ideas, that's how the science will become a diverse field. And then you can say, oh, I know about this paper. If something is not published, there is no way for the vast majority of scientists to learn about this thing. You know, there's no way.
And I mean, as somebody, look, I work as a structural engineer, so obviously I'm not, this field is just an interest of mine, like other fields as well. You know, it's helpful to have an open forum and an open, you know, peer review process or open review process. I mean, I agree, clear mathematical errors, maybe you can reject it on that basis. But anything else, I feel that the people who are knowledgeable about the field will know who writes better papers than others. They would know, you know, what to read and what not to read. And at the end of the day, you know, I mean, if you go back to, say, material science, which I know quite well, there was a European tradition and an English tradition that developed parallel with each other. One was more abstract and theoretical, and one was more empirical. And at the end of the day, both of them added value to the field, right? But completely different parts of fields. And I don't mind there being different scientific paradigms. There can be half the climate scientists who believe in the greenhouse effect, and half of them believe in what you're saying, and the other half don't believe anything. So what? It will be much better if there is this more pluralism in the field.
Well, it's like a market economy. Now you have a competition of different ideas and different goods. The market economy, and the ones that have the quality and the right price wins, right? And in the case of science, the one that actually is supported by the data and people see that this makes sense, not only theoretically but observationally, then it works. But when you have a politically motivated science, then they have an agenda to keep one theory alive and suppress everything else. Then a free dialogue like this becomes dangerous, becomes inconvenient, not dangerous, but inconvenient for the political elite, because it can expose the truth that what they support politically is actually physically incorrect, which is the case in this case. Think about this world has been turned upside down, to stop climate change. They use terms like stop climate change, prevent climate change. It's like talking about stopping gravity. It's the conversation.
But it's even stupid, because climate change, I mean, if you said stop global warming, at least you might have a case. Okay, at least there's a way to do it. But what the hell is climate change? It's such a vacuous propaganda statement to begin with.
Climate change was a term that replaced global warming after they realized that the warming slowed down or stopped at some point.
No, it was introduced by CNN to blame any weather event on climate change, so they could sell the newspapers and scare the hell out of kids. But it's completely idiotic. And yet we have the world leaders. It is in international law now. Climate change. Something as idiotic as that has gotten that far. But what do I know?
Climate change is real because climate is always changing. The point is that we have no control over it, and to try to do something about it and to change our economy and our style of living.
But this has been a demand for people to build their careers on. It's sort of like terrorism. Okay, I know what your politics might be, but we're going to fight terrorism. Well, you cannot really destroy it. It's as idiotic, the idea, but it sells. It's like fighting piracy. It's an idea. You cannot go to war against an idea. But anyway, so climate change is one of them. This is one of them. It's like the war against cancer, by the way, which is even worse than global warming. I've looked into that one. There's a good case to make that cancer is not caused by genes, by gene mutation.
No, it's not. It's a metabolic disease, yes.
Yeah, it's metabolic disease. So there's a lot of other stuff like that as well. Again, you cannot criticize it because the money is going into one direction and it keeps the paradigm alive. So we need to rethink the incentive structures of how we fund science.
Like with everything, they say follow the money and you'll find out the cause.
So I'd like to thank the two of you, and it's been really interesting conversation. And I hope the climate skeptics at least give you a little bit more airtime.